Tonight, we're going to explore something invisible, something you've never seen, never touched, never heard. And yet, this invisible thing is the only reason you're alive right now. It's the reason life exists on Earth at all. We're going to talk about Earth's magnetic field, the quiet shield that wraps around our planet like a protective bubble, deflecting dangers from space that would otherwise strip away our atmosphere, scorch the surface, and leave Earth as barren as Mars. By the end of this journey, you're going to understand how this invisible force works, where it comes from, and what would happen if it suddenly disappeared. You'll learn about solar storms, ancient magnetic reversals, and the spectacular light shows that happen when space weather collides with our planet's defenses. Before we begin, if you enjoy these calm explorations of science and mystery, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a real difference for me. Now, let's start our journey into the invisible. Let's begin with something you probably take for granted. Right now, as you listen to these words, you're surrounded by a magnetic field. You can't feel it. You can't see it. Most of the time, you don't even think about it, but it's there, extending thousands of miles above your head and deep into the ground beneath your feet. This field is ancient, older than the continents, older than the oceans. It's been protecting Earth for billions of years, working silently, asking nothing in return. The magnetic field doesn't make noise. It doesn't glow. It doesn't announce its presence. And yet, without it, you wouldn't be here. Neither would anyone else. Life as we know it depends entirely on this invisible force. Think about that for a moment. Something you've never noticed, something completely outside your awareness, is the single most important thing standing between Earth and cosmic destruction. The first humans to notice Earth's magnetic field didn't understand what they were seeing. Ancient Chinese navigators, over 2,000 years ago, discovered that certain stones, when suspended or floated on water, would always point in the same direction. They called these lodestones, naturally magnetized pieces of magnetite. They didn't know why these stones behaved this way. They didn't understand the physics, but they recognized the pattern. The stone always pointed north. Always. This was useful. If you were traveling across unfamiliar land or sailing across open water, you could use a lodestone to find your direction. You could orient yourself. The compass was born from this observation, one of humanity's most important navigational tools, and it worked because Earth itself is a giant magnet. For centuries, people used compasses without understanding why they worked. The compass needle pointed north. That was enough. Sailors crossed oceans. Explorers mapped continents. Armies marched in formation, all guided by this mysterious force that pulled on magnetized metal. It wasn't until the 16th century that someone tried to explain it. William Gilbert, an English physician and natural philosopher, published a book in 1600 called De Magnete. In it, he proposed something radical. He suggested that Earth itself was a massive magnet with its own north and south poles. This was revolutionary thinking. Gilbert performed experiments with spherical lodestones, which he called Terrellas, little Earths. He showed that a compass needle would align itself with these spheres in the same way it aligned with Earth. From this, he concluded that Earth's magnetism was intrinsic, part of the planet itself, not something imposed from outside. Gilbert was right, though he didn't understand the mechanism. He thought the magnetism came from Earth's iron core, which was partially correct. But the full story is more complex and more fascinating. Here's what we know now. Deep inside Earth, about 1,800 miles beneath your feet, there's an outer core made of liquid iron and nickel. This molten metal is incredibly hot, thousands of degrees, and it's constantly moving. The movement isn't random. It's driven by heat from the even deeper inner core and by the rotation of the planet. As Earth spins, the liquid metal swirls and flows in complex patterns. This moving, electrically conductive fluid generates electric currents, and when electric currents flow, they create magnetic fields. This process is called the geodynamo, It's a self-sustaining system. The motion of the liquid metal generates the magnetic field, and the magnetic field influences the motion of the metal. The two feed into each other, creating a stable, long-lasting magnetic field that extends far beyond the planet's surface. This field isn't static. It's always changing, always shifting, responding to the churning motions deep inside Earth. But on human timescales, it seems stable. It's been there your whole life, your parents' whole lives, your grandparents' whole lives. It feels permanent, but it's not. The magnetic field isn't perfectly aligned with Earth's geographic poles. The magnetic North Pole, the point where compass needles point, is not the same as the true North Pole, the axis around which Earth rotates. Right now, the magnetic North Pole is located in the Canadian Arctic, but it's moving. Every year, it drifts about 34 miles toward Siberia. This movement has been accelerating recently. Scientists aren't entirely sure why. The magnetic field is complex, generated by chaotic flows of molten iron thousands of miles below the surface. Small changes in those flows can shift the location of the poles. This drift has practical consequences. Navigation systems, aviation charts, and GPS satellites all have to account for the changing position of magnetic north. If they didn't, compasses would slowly become inaccurate, leading ships and planes off course. The magnetic South Pole is also drifting, though not as quickly. It's currently off the coast of Antarctica, wandering across the Southern Ocean. These poles aren't fixed points. They're dynamic, responding to the invisible forces churning beneath the surface. But here's the really important part. The magnetic field doesn't just help you navigate, it protects you. Every second of every day, the sun is bombarding Earth with a stream of charged particles. This is called the solar wind. A constant flow of electrons, protons, and other atomic fragments blasted away from the sun's surface at speeds of over 1,000,000 miles per hour. The solar wind reaches Earth in about 3 to 4 days. When it arrives, it slams into Earth's magnetic field. And that's when something extraordinary happens. The magnetic field deflects most of these particles, bending them around the planet, guiding them away. Without this deflection, the solar wind would hit Earth's atmosphere directly. Over time, it would strip away the atmosphere molecule by molecule, the way it did on Mars. Mars once had a thick atmosphere, possibly even liquid water on its surface. But Mars lost its magnetic field billions of years ago. Without that protection, the solar wind gradually eroded the Martian atmosphere, leaving behind the thin, cold, barren world we see today. Earth would have suffered the same fate if not for the magnetic field. You can actually see this protection in action, though most people don't realize what they're looking at. Have you ever seen the Northern Lights, the Aurora Borealis, or the Southern Lights, the Aurora Australis? Those shimmering curtains of green, red, and purple light that dance across the sky near the poles are a direct result of the magnetic field at work. Here's how it happens. When the solar wind encounters Earth's magnetic field, most particles are deflected, but some get funneled along the field lines toward the north and south magnetic poles. As these particles descend into the upper atmosphere, they collide with oxygen and nitrogen, molecules. Those collisions transfer energy to the atmospheric gases, exciting them, causing them to emit light. Oxygen produces green and red hues. Nitrogen produces blue and purple. The result is one of nature's most spectacular displays, a visible reminder of the invisible shield protecting us. The auroras aren't just beautiful, they're evidence that the magnetic field is working, deflecting the solar wind, guiding particles away from the equator and toward the poles where the atmosphere can absorb them safely. But not all solar weather is routine. Sometimes, the sun releases something far more powerful than the usual solar wind. These are called solar storms, massive eruptions of energy and matter from the sun's surface. The most intense are coronal mass ejections, or CMEs. A single CME can hurl billions of tons of plasma into space at speeds of several million miles per hour. If a large CME is aimed at Earth, it can overwhelm even the magnetic field's defenses. When that happens, the consequences can be severe. Satellites can be damaged or destroyed. Power grids can fail. Communication systems can go down. In 1859, a massive solar storm called the Carrington Event struck Earth. It was the most powerful geomagnetic storm ever recorded. Telegraph systems around the world failed. Operators reported sparks flying from their equipment. Some telegraph lines caught fire. Auroras were seen as far south as the Caribbean. If a storm of that magnitude hit today, it could cause trillions of dollars in damage, knocking out electrical grids, disabling satellites, and disrupting GPS, internet, and communications for months or even years. And here's the unsettling part. We know it will happen again. We just don't know when. Are you starting to see why the magnetic field matters? It's not just a scientific curiosity. It's not just something that makes compasses work. It's the difference between a living planet and a dead one. It's the reason our atmosphere is, still here. The reason water didn't boil away into space billions of years ago. The reason life had a chance to evolve and thrive. And yet, for most of human history, we didn't even know it existed. We walked on a planet wrapped in an invisible shield, completely unaware of the dangers being deflected above our heads. Now that you know, the next time you look up at the night sky, you can think about what's happening up there in the invisible space between Earth and the Sun. Charged particles racing toward you at 1,000,000 miles per hour, only to be gently turned aside by a force you'll never see. And here's the question I want you to think about as we continue this journey. If the magnetic field is so important, so essential to life, what happens when it changes? What happens when it weakens or shifts or disappears entirely? Because that's not a hypothetical question. It's happened before, and it could happen again. Have you ever wondered what it would feel like to live through a magnetic reversal, when north becomes south and the invisible shield protecting Earth flickers and fades, even if just for a moment? We'll explore that mystery soon. Let's talk about something that sounds like science fiction but is actually scientific fact. Earth's magnetic field has reversed itself multiple times. North became south, south became north. The compass needle that pointed one way for millions of years suddenly pointed the opposite direction. And life on Earth? It survived. But how? And more importantly, when will it happen again? The first clues came from rocks. In the early 20th century, geologists studying ancient lava flows noticed something strange. When lava cools and solidifies, tiny magnetic minerals inside the rock align themselves with Earth's magnetic field at that moment, like millions of microscopic compass needles freezing in place. Once the rock hardens, that magnetic signature is locked in permanently. It becomes a record, a snapshot of Earth's magnetic field at the time the lava cooled. And here's what confused scientists. Some rocks had their magnetic minerals pointing north, exactly as you'd expect. But other rocks, from different time periods, had their minerals pointing south. Not a little bit south, completely reversed, as if Earth's magnetic poles had flipped 180 degrees. At first, researchers thought these reversed rocks must be anomalies, local magnetic disturbances or measurement errors. But as they collected more samples from locations all over the world, a pattern emerged. The reversals weren't random. They weren't isolated incidents. They were global. Rocks of the same age on different continents showed the same reversal pattern. This meant something profound. At certain points in Earth's history, the entire magnetic field had flipped. North and south had switched places. The evidence was undeniable, and it raised an uncomfortable question. If it happened before, could it happen again? And if it did, what would that mean for us? Scientists began mapping these reversals, creating a timeline of Earth's magnetic history. They studied the ocean floor, where new crust is constantly being formed at mid-ocean ridges. As magma wells up from the mantle and cools, it records the current magnetic field. Over millions of years, the seafloor spreads outward from these ridges, creating parallel stripes of rock with alternating magnetic orientations. Normal polarity, reversed polarity, normal, reversed. The pattern repeats like a barcode. each stripe representing a different magnetic epoch. By analyzing these magnetic stripes, geologists reconstructed Earth's magnetic history going back hundreds of millions of years. What they found was remarkable. The magnetic field has reversed hundreds of times. Sometimes the reversals happen quickly, geologically speaking. Other times, the field remained stable for millions of years before flipping again. The last reversal, called the Brunhes-Matuyama reversal, occurred about 780,000 years ago. Before that, Earth's magnetic field had the opposite polarity for about 600,000 years. Here's what makes this particularly interesting. The reversals aren't predictable. There's no regular pattern, no consistent interval. Sometimes millions of years pass between reversals. Other times, they happen more frequently. During one period, called the Cretaceous Normal Superchron, the magnetic field didn't reverse at all for nearly 40 million years. Then, during other periods, reversals happened every few 100,000 years. Scientists don't fully understand why. The geodynamo, that churning mass of molten iron deep inside Earth, operates according to complex physics. Slight changes in temperature, rotation, or flow patterns can trigger a reversal. But predicting when the next one will occur is nearly impossible. The system is too chaotic, too sensitive to small variations. We can say with certainty that it will happen eventually. We just can't say when. And here's the unsettling part. There are signs that we might be approaching another reversal. The magnetic field has been weakening. Over the past 200 years, the field strength has decreased by about 9%. That might not sound like much, but it's significant. In some regions, particularly over the South Atlantic, the field is especially weak, creating what scientists call the South Atlantic anomaly. Satellites passing through this region experience higher levels of radiation. The weakening field allows more charged particles from space to penetrate closer to Earth's surface. Some researchers believe this weakening could be the early stage of a reversal. Others think it's just normal variation, part of the magnetic field's constant fluctuations. The truth is, we don't know. We've never observed a reversal in real time. We've only studied the aftermath in ancient rocks. We don't know what it looks like when it actually happens. So, what would a magnetic reversal look like if it happened during your lifetime? First, understand that it wouldn't be instantaneous. The magnetic field wouldn't just flip from one day to the next. Based on geological evidence, reversals take hundreds or even thousands of years to complete. During that transition, the magnetic field would become chaotic. Instead of one clear north pole and one south pole, multiple magnetic poles might appear and disappear at different locations around the planet. The field strength would fluctuate wildly. In some areas, the field might nearly vanish. In others, it might strengthen temporarily. Compasses would become unreliable, pointing in different directions depending on where you were standing. Navigation systems that rely on Earth's magnetic field would need constant recalibration. But the real danger wouldn't be to navigation. It would be to the protective shield itself. During a reversal, when the magnetic field weakens and becomes disorganized, Earth's protection from solar radiation diminishes. More charged particles from the solar wind would penetrate deeper into the atmosphere. The auroras, those beautiful lights usually confined to the polar regions, might appear at lower latitudes, perhaps even near the equator. But this wouldn't just be a light show. Increased radiation could damage satellites more frequently. Power grids could experience more disruptions. Communication systems could suffer more interference. And if a major solar storm hit during the transition period, when the magnetic field was at its weakest, the consequences could be severe. Without the full strength of the magnetic shield, a large coronal mass ejection could cause widespread blackouts, destroy critical infrastructure, and expose high-altitude flights to dangerous radiation levels. The 1859 Carrington event happened when Earth's magnetic field was at normal strength. Imagine a similar storm hitting during a reversal, when the field is a fraction of its usual power. But here's the question scientists keep asking. If magnetic reversals have happened hundreds of times in Earth's history, why didn't they wipe out life? You'd think that losing the magnetic shield, even temporarily, would be catastrophic. And yet, when researchers look at the fossil record, they don't see mass extinctions coinciding with magnetic reversals. Life continued. Species evolved. The biosphere adapted. Some studies have suggested minor increases in extinction rates during certain reversals, but nothing approaching the devastation caused by asteroid impacts or massive volcanic eruptions. This is one of the great mysteries of magnetic reversals. They seem dangerous in theory, but in practice, life has survived them repeatedly. Why? One possibility is that the magnetic field never completely disappears, even during a reversal. It weakens, yes. It becomes chaotic, yes. But some level of protection remains. Even a partial shield is better than no shield at all. Another possibility is that Earth's atmosphere provides additional protection. The atmosphere absorbs much of the incoming radiation, especially the lower atmosphere where most life exists. Ocean-dwelling creatures would have even more shielding, protected by both the atmosphere and the water above them. There's also the question of timescale. Reversals happen slowly enough that life can adapt. If the transition takes 1,000 years, that's plenty of time for organisms to adjust to gradually changing conditions. Species that rely on magnetic navigation, like migratory birds and sea turtles, might struggle during the transition period. These animals use Earth's magnetic field to orient themselves during long-distance journeys. If the field became unreliable, their navigation would be disrupted. Some individuals might get lost. Populations could decline, but given enough time, evolution would favor individuals with alternative navigation strategies, perhaps relying more on visual landmarks or the position of the sun and stars. Life is remarkably resilient. It finds a way, even when the invisible forces it depends on become unstable. Still, there's a difference between life surviving a reversal in the past and modern civilization surviving one today. Ancient organisms didn't rely on satellites, GPS, electrical grids, or global communication networks. We do. A magnetic reversal in the modern age would be a technological challenge unlike anything humanity has faced. We'd need to redesign satellites to withstand higher radiation levels. We'd need to protect power grids from geomagnetic storms. We'd need backup navigation systems that don't rely on the magnetic field. We'd need to monitor solar activity more closely than ever, forecasting dangerous space weather with enough warning to take protective measures. In some ways, we're better prepared than any previous generation. We understand what's happening. We can see it coming, at least in a general sense. But in other ways, we're more vulnerable because we've built a global civilization on infrastructure that assumes a stable magnetic field. That assumption might not hold forever. Let me give you a sense of what we're actually talking about when we say the magnetic field protects us. Right now, above your head, there's a region of space called the magnetosphere. This is the area dominated by Earth's magnetic field, extending tens of thousands of miles into space. The magnetosphere isn't spherical, despite the name. It's shaped more like a teardrop, compressed on the side facing the sun and stretched into a long tail on the opposite side. This asymmetry is caused by the solar wind. As the stream of charged particles from the sun hits the magnetosphere, it pushes against it, compressing the field lines on the day side. On the night side, away from the sun, the field lines stretch out into space, forming a magnetotail that extends beyond the moon's orbit. Inside this magnetosphere, Earth is relatively safe. Outside it, space is filled with radiation, high-energy particles that would be deadly to unprotected living tissue. Astronauts in low Earth orbit, inside the magnetosphere, receive some protection. But astronauts traveling to the Moon or Mars leave this protective bubble. They're exposed to much higher radiation levels, which is one of the major challenges for long-duration space missions. The boundary between the magnetosphere and the solar wind is called the magnetopause. This is where the two forces meet and balance. On one side, Earth's magnetic field pushes outward. On the other side, the solar wind pushes inward. The magnetopause shifts position constantly, responding to changes in solar wind pressure. During intense solar storms, the magnetopause can be pushed much closer to Earth, shrinking the magnetosphere. During calm periods, it expands outward. This boundary isn't a solid wall. It's more like a dynamic interface, a region where particles and energy are exchanged, where the invisible forces of Earth and Sun wrestle for dominance. And most of the time, Earth wins. The magnetic field holds the line, deflecting the solar wind, preserving the atmosphere, maintaining the conditions that allow life. To understand what powers Earth's magnetic field, we need to go deeper, much deeper. Imagine descending through the layers of the planet, past the solid crust where we live, through the mantle with its slow-moving currents of rock, down into the core itself. This is a journey no human could ever make. The pressure would crush you instantly. The heat would vaporize you long before you reach the center. But we can travel there in our minds, guided by the evidence scientists have pieced together over decades of patient observation. The journey begins at the surface. The crust, the thin outer shell of rock we call home, is only about 5 to 40 miles thick depending on location. Thinner under the oceans, thicker under the continents. If Earth were an apple, the crust would be thinner than the skin. And yet, this is where all of human history has unfolded. Every city, every mountain, every ocean floor exists within this impossibly thin layer. Beneath the crust lies the mantle, a vast region of hot, dense rock extending down about 1,800 miles. The mantle isn't liquid exactly. It's solid rock, but under the immense pressure and heat, it behaves more like an extremely thick fluid, flowing slowly over millions of years. This flow drives plate tectonics, the movement of continents, the formation of mountains, the eruption of volcanoes. The mantle is dynamic, constantly churning, transferring heat from the core toward the surface. And then, at about 1,800 miles down, you reach the outer core. This is where the story of Earth's magnetic field truly begins. The outer core is liquid, a seething ocean of molten iron and nickel at temperatures around 7,000 to 9,000 degrees Fahrenheit. That's as hot as the surface of the sun. At these temperatures and pressures, iron remains liquid, flowing in complex patterns driven by heat from below and the rotation of the planet above. This isn't a calm lake. It's turbulent, chaotic, with currents and eddies and flows that operate on timescales ranging from years to millions of years. The outer core is about 1,400 miles thick, a vast reservoir of liquid metal surrounding the innermost part of the planet. At the very center, about 3,200 miles beneath your feet, lies the inner core. This is solid iron, crystallized under unimaginable pressure. The inner core is roughly 760 miles in radius, about the size of the moon. Despite being even hotter than the outer core, reaching temperatures up to 10,800 degrees Fahrenheit, the pressure is so intense that the iron cannot remain liquid. It's forced into a solid state, a giant iron crystal slowly rotating, slightly out of sync with the rest of the planet. The inner core grows very slowly over geological time as the Earth gradually cools and more iron crystallizes out of the outer core. This growth releases heat, and that heat is crucial to the geodynamo. Here's how the geodynamo works. Heat flows outward from the inner core into the outer core. This creates temperature differences in the liquid iron, and those temperature differences drive convection currents. Just like water boiling in a pot. Hot liquid iron rises from the inner boundary of the outer core. As it rises, it cools slightly and eventually sinks back down. This up and down motion creates circulation patterns within the outer core. But there's another factor at play. Earth is rotating. As the liquid iron circulates, the planet's rotation twists and deflects the flow patterns, a phenomenon called the Coriolis effect. The same effect that influences weather patterns and ocean currents on the surface also shapes the motion of molten metal thousands of miles below. The combination of convection and rotation creates spiraling flows within the outer core. Now, here's where the magnetism comes in. Liquid iron is electrically conductive. When it moves through an existing magnetic field, it generates electric currents. And when electric currents flow through a conductor, they create their own magnetic fields. So, the moving liquid iron generates a magnetic field, and that magnetic field influences the motion of the iron, which generates more magnetic field, which influences the motion further. It's a self-reinforcing loop, a dynamo. As long as the outer core remains liquid and in motion, the geodynamo continues operating, sustaining Earth's magnetic field. This process has been running for billions of years, probably since shortly after Earth formed. The magnetic field is ancient, a fundamental property of the planet, as long-lasting as the continents and oceans. But nothing lasts forever. Eventually, Earth will cool. The heat driving the convection in the outer core comes from two main sources. One is primordial heat, left over from the planet's formation when countless collisions of rocks and debris released enormous amounts of energy. The other is radioactive decay, the slow breakdown of radioactive elements like uranium, thorium, and potassium within Earth's interior. These elements release heat as they decay, and that heat has been warming the planet from the inside for billions of years. But radioactive elements don't last forever. They decay into stable forms, releasing less and less heat over time. And Earth, despite being geologically active, is gradually cooling. Very slowly, over billions of years, but cooling nonetheless. As Earth cools, the inner core grows. More and more iron crystallizes out of the outer core, expanding the solid center. This actually helps sustain the geodynamo for now, because the crystallization process releases latent heat, which drives convection in the outer core. But eventually, if cooling continues, the entire core could solidify. When that happens, the motion of liquid iron would cease. The electric currents would stop. The magnetic field would collapse. Earth would become like Mars, a planet without a magnetic shield. The atmosphere would be vulnerable to erosion by the solar wind. Over millions of years, Earth could lose its oceans, its air, its ability to support life. But don't worry, this won't happen for billions of years. By the time Earth's core fully solidifies, the sun will likely have already expanded into a red giant, engulfing the inner planets. Earth's magnetic field will outlive us, our species, and quite possibly all life on the planet. Still, the fact that it's temporary at all is sobering. The magnetic field feels eternal, unchanging, as permanent as the ground beneath your feet. But it's not. It's a dynamic process sustained by the slow cooling of a planet, powered by heat from radioactive decay and primordial energy, operating on a timescale so vast that human lifetimes are barely a flicker. And yet, it can change. It can weaken, reverse, or even disappear if the conditions are right. Other planets offer us cautionary tales. Mars, as I mentioned, lost its magnetic field billions of years ago, probably because its smaller size caused it to cool faster than Earth. Without the protection of a magnetic field, Mars's atmosphere was gradually stripped away, leaving the cold, dry, barren world we see today. Venus, on the other hand, never had a strong magnetic field. Or if it did, it lost it very early in its history. Venus is roughly the same size as Earth, but it rotates extremely slowly, taking 243 Earth days to complete one rotation. This slow rotation might prevent the formation of a strong geodynamo. Without a magnetic field, Venus's thick atmosphere is exposed directly to the solar wind. Though in Venus's case, the atmosphere is so dense that it provides its own form of protection, albeit a very different environment than Earth's. Mercury, the smallest planet and closest to the Sun, does have a magnetic field, but it's much weaker than Earth's. Only about 1% is strong. Scientists aren't entirely sure how Mercury generates its field. The planet is so small that its core should have cooled and solidified by now, shutting down any geodynamo. But measurements from spacecraft show a definite magnetic field, which suggests that at least part of Mercury's core is still liquid and in motion. It's a mystery, one of many in planetary science. Each planet is an experiment in magnetic field generation, governed by size, composition, rotation rate, and internal heat. Earth happened to get the right combination of factors to sustain a strong, long-lasting magnetic field. We're lucky in that regard. Let me take you back to the question of magnetic reversals for a moment, because there's more to this story. Scientists have been trying to figure out exactly how a reversal happens at the level of the geodynamo. What changes in the outer core to make the magnetic field flip? The answer, as far as we understand it, has to do with instabilities in the flow of molten iron. Imagine the outer core as a chaotic system, with multiple circulation patterns happening simultaneously. Most of the time, these flows are organized in a way that reinforces a stable magnetic field, with one north pole and one south pole. But occasionally, the flows become disorganized. Small eddies and turbulent regions grow in strength. These localized disturbances can create their own small magnetic fields with reversed polarity. If these reversed regions become strong enough and widespread enough, they can overwhelm the main magnetic field, causing it to collapse and reorganize with the opposite polarity. The transition period, when the old field is collapsing and the new field is forming, is when we'd see a weakened, chaotic magnetic field with multiple poles appearing and disappearing. Computer simulations of the geodynamo have actually reproduced magnetic reversals. Researchers can model the flow of liquid iron in Earth's core using complex mathematical equations and powerful supercomputers. When they run these simulations over long timescales, the virtual magnetic field spontaneously reverses itself every few 100,000 years, just like the real thing. This is remarkable. It means we don't need to invoke any external trigger for reversals. No asteroid impacts. No changes in Earth's rotation, no outside influence. Reversals are an inherent property of the geodynamo itself, an inevitable consequence of the chaotic, turbulent nature of the molten iron flows. The system is self-organizing but also self-disrupting. It creates order, the stable magnetic field, but that order is always vulnerable to being overthrown by the underlying chaos. There's something almost poetic about that, don't you think? The magnetic field that protects us, that makes life possible, that shields us from the dangers of space, is itself the product of chaos. Deep beneath our feet, in a realm we'll never visit, molten metal churns and flows according to the laws of physics, occasionally reorganizing itself in ways that flip the entire magnetic field. And through all of this chaos, life on the surface continues, mostly unaware, mostly unaffected. It's a reminder that the universe doesn't care about us. The processes that sustain our existence, the magnetic field, the atmosphere, the sun's steady burning, they operate according to their own logic. We're passengers on this planet, benefiting from conditions we didn't create and can't control. But here's where human ingenuity comes into play. Even though we can't control the geodynamo, we can understand it, we can measure it, we can predict, to some extent, how it will behave, and we can prepare for the consequences. Over the past few decades, scientists have built a network of observatories around the world dedicated to monitoring Earth's magnetic field. These observatories measure the field's strength, direction, and variations with incredible precision. Satellites orbiting above the atmosphere add another layer of data, mapping the global structure of the magnetosphere and tracking changes over time. One of the most important of these satellites is the European Space Agency's SWARM mission, a constellation of 3 satellites launched in 2013. SWARM measures Earth's magnetic field from orbit, creating detailed maps of how the field changes over days, months, and years. The data from SWARM has revealed new details about the geodynamo, including evidence of rapid changes in the flow of molten iron in the outer core. One particularly intriguing discovery is something called geomagnetic jerks. These are sudden changes in the rate at which the magnetic field is changing. Normally, the magnetic field shifts gradually, drifting slowly over decades. But occasionally, the rate of change itself changes abruptly. The field might be weakening at a steady rate, and then suddenly, over the course of a year or less, the rate of weakening increases or decreases. These jerks are thought to be caused by rapid changes in the flow patterns within the outer core, possibly the acceleration or deceleration of specific currents. They're evidence that the core is dynamic, not static, capable of shifting its behavior on relatively short timescales. Studying these jerks helps scientists understand how the geodynamo operates and might even provide early warning signs of a future magnetic reversal. The South Atlantic anomaly, which I mentioned earlier, is another feature that scientists are watching closely. This is a region over the South Atlantic Ocean where the magnetic field is significantly weaker than elsewhere on Earth. The anomaly has been growing and intensifying over the past few decades. Some researchers think it might be a precursor to a magnetic reversal, a sign that the field is beginning to destabilize. Others believe it's just a normal fluctuation, part of the magnetic field's constant variation. The truth is, we don't have enough data yet. We've only been measuring the magnetic field with modern instruments for a few hundred years, and we've only had satellite data for a few decades. That's not nearly enough time to distinguish between normal variation and the early stages of a reversal. We're trying to understand a process that unfolds over thousands of years using only a century or two of detailed observations. It's like trying to predict the weather next year by looking at a single day's data. Still, the effort is worthwhile. Understanding the magnetic field and the geodynamo is one of the great challenges in Earth science. It requires knowledge of fluid dynamics, electromagnetism, geology, and planetary science. It requires observations from the surface, from orbit, and from indirect measurements of the deep interior. And it requires patience, waiting for decades or even centuries of data to accumulate, slowly building a clearer picture of how this invisible shield operates. The magnetic field connects the deepest interior of the planet to the farthest reaches of the magnetosphere. It links processes happening thousands of miles below your feet to phenomena occurring tens of thousands of miles above your head. It's a planetary scale system, and we're still learning how all the pieces fit together. Think about this for a moment. You're standing on the surface of a planet. Beneath you, thousands of miles down, liquid iron is flowing in complex patterns, generating a magnetic field. That field extends out into space, creating a protective bubble around the planet. The Sun, 93 million miles away, is constantly sending a stream of charged particles toward Earth. Those particles collide with the magnetosphere, are deflected. Some are trapped in radiation belts. Others funnel down to the poles where they create auroras. All of this is happening right now, has been happening for billions of years, and will continue happening for billions more. And most of the time, you don't think about it. You go about your day, completely unaware of the invisible forces at work around you. That's okay. The magnetic field doesn't need your attention to keep functioning. But now that you know, doesn't it change how you see the world? Doesn't it add a layer of wonder to something as simple as looking up at the night sky? If you could somehow see the magnetic field, what would it look like? The field lines would arc out from the south magnetic pole, curve through space, and descend back into the north magnetic pole. Near the surface, close to the poles, the field lines would be nearly vertical, pointing straight down in the north and straight up in the south. At the equator, the field lines would be horizontal, running parallel to the ground. If you could see the magnetosphere from space, you'd see this teardrop-shaped bubble, compressed on the side facing the sun, stretched into a long tail on the opposite side. You'd see the solar wind streaming past, particles flowing around the magnetosphere like water around a rock in a stream. You'd see the auroral ovals, glowing rings around the magnetic poles where particles rain down into the atmosphere. It would be beautiful, a dynamic, ever-changing sculpture of invisible forces made visible. But of course you can't see any of this. The magnetic field is invisible to human eyes. We experience its effects, the working compass, the shimmering auroras, the protection from radiation, but the field itself remains hidden. And maybe that's part of what makes it so fascinating. The most important protective system on the planet is something we'll never directly perceive. We can measure it, model it, understand it intellectually, but we can't see it, touch it, or feel it. It's a reminder that reality is richer and more complex than our senses reveal. There are forces at work all around us, shaping our world, making our existence possible, and we navigate through them mostly blind. relying on instruments and mathematics to show us what's there. So, where does this leave us as we continue our journey? We've explored what the magnetic field is, how it's generated, how it protects us, and how it changes over time. We've seen that it's powered by the slow cooling of Earth's core, driven by convection in the outer core, and sustained by the geodynamo, a self-reinforcing loop of motion and magnetism. We've learned that the field has reversed hundreds of times in the past and will almost certainly reverse again in the future, though we can't predict when. We've discovered that the field is weakening in some regions, particularly over the South Atlantic, and that scientists are monitoring these changes closely to better understand what might happen next. But there's more to this story. The magnetic field doesn't just protect us from the solar wind. It also protects us from cosmic rays, high-energy particles from outside the solar system. And when the sun releases a particularly powerful solar storm, the interaction between solar energy and Earth's magnetic field can be spectacular and dangerous. In the next part of our journey, we'll explore these solar storms in more detail, what causes them, how they interact with the magnetosphere, and what happens when the shield is breached. We'll also look at the auroras more closely, those beautiful lights that are the visible signature of the magnetic field at work. Do you think the ancients who saw the northern lights had any idea they were witnessing the collision of solar particles with Earth's protective shield? Or did they imagine something entirely different, something magical, something divine? The sun is both our greatest friend and our greatest threat. Without it, Earth would be a frozen ball of ice drifting through the darkness of space. But the sun is not calm. It's a roiling sphere of plasma, constantly erupting, constantly releasing energy and matter into space. And sometimes, those eruptions are aimed directly at us. Let's start with what the sun actually is. It's a massive ball of hydrogen and helium, held together by its own gravity, with nuclear fusion happening at its core. Every second, the sun converts about 600 million tons of hydrogen into helium through fusion reactions that release enormous amounts of energy. That energy works its way outward from the core, taking thousands of years to reach the surface, where it's finally released as light and heat. The surface of the sun, the part we can see, is called the photosphere. It has a temperature of about 10,000 degrees Fahrenheit. But the sun doesn't end at the photosphere. Above it lies the chromosphere, a thin layer of hot gas, and above that, the corona, an extended atmosphere of extremely hot plasma reaching temperatures of several million degrees. Why the corona is so much hotter than the surface below, it is still not fully understood. It's one of the great mysteries of solar physics. The sun's magnetic field is incredibly complex. Unlike Earth's relatively organized field with clear north and south poles, the sun's magnetic field is tangled, twisted, and constantly changing. This is because the sun isn't solid. It's a ball of plasma, ionized gas where electrons have been stripped from atoms by the intense heat. Plasma conducts electricity, and when electrically conductive material moves through a magnetic field, it generates electric currents, which create their own magnetic fields. The sun rotates, but not uniformly. The equator rotates faster than the poles, completing one rotation in about 25 days compared to about 35 days at the poles. This differential rotation stretches and twists the magnetic field lines, wrapping them around the sun like rubber bands being wound tighter and tighter. Eventually, these twisted field lines become unstable. They can break through the surface, creating sunspots, dark patches on the photosphere where the magnetic field is particularly strong. Sunspots are cooler than the surrounding surface, which is why they appear dark, but they're still incredibly hot, around 6,500 degrees Fahrenheit. Sunspots are often where solar eruptions originate. The twisted magnetic field lines store enormous amounts of energy, like a compressed spring. When the field becomes too twisted, too unstable, it can suddenly release that energy in an explosive event. There are two main types of solar eruptions: solar flares and coronal mass ejections. Solar flares are intense bursts of radiation, X-rays, and ultraviolet light that travel from the sun to Earth at the speed of light. They reach us in about 8 minutes, When a large flare erupts on the side of the sun, facing Earth, the burst of radiation can interfere with radio communications, disrupt GPS signals, and even damage satellites. Fortunately, Earth's atmosphere absorbs most of this radiation, so people on the ground are protected. But astronauts in space or high-altitude airline passengers can receive increased radiation exposure during major flares. Coronal mass ejections, or CMEs, are different and potentially more dangerous. A CME is a massive eruption of plasma and magnetic field from the sun's corona. When a CME erupts, it hurls billions of tons of solar material into space at speeds ranging from a few hundred to several thousand miles per second. If a CME is directed toward Earth, it can take anywhere from 15 hours to several days to arrive, depending on its speed. When it hits, the interaction with Earth's magnetic field can be dramatic. The CME's magnetic field collides with Earth's magnetosphere, compressing it, distorting it, and in some cases, temporarily overwhelming it. This is called a geomagnetic storm, and depending on its intensity, the effects can range from beautiful auroras to widespread technological disruption. Let me describe what happens during a major geomagnetic storm. As the CME approaches Earth, its leading edge, a shockwave of compressed plasma, slams into the magnetopause. The impact compresses the magnetosphere, pushing the boundary closer to Earth. The magnetic field from the CME can have any orientation, but if it happens to point south, opposite to Earth's magnetic field, the two fields can reconnect, a process where the field lines merge and release energy. This reconnection allows solar particles to enter the magnetosphere more easily. The magnetotail, that long extension of the magnetic field on the night side of Earth, becomes energized. Magnetic field lines in the tail snap and reconnect, accelerating particles toward Earth. These particles spiral down along the field lines toward the magnetic poles, colliding with the atmosphere and creating auroras. During a severe geomagnetic storm, the auroras can be seen much farther from the poles than usual. Normally, you'd need to be in Alaska, northern Canada, Scandinavia, or other high-latitude regions to see the northern lights. But during a major storm, auroras have been observed as far south as the Caribbean, Mexico, even Hawaii. Historical records describe red and green lights filling the sky, bright enough to read by, appearing in places where they'd never been seen before. People who had no idea what auroras were thought the sky was on fire, or that the end of the world was near. In ancient times, without scientific understanding, these lights must have seemed supernatural, divine messages or omens. The most famous geomagnetic storm in recorded history is the Carrington event of 1859. On September 1st of that year, British astronomer Richard Carrington was observing sunspots when he witnessed a massive solar flare, a bright flash of light erupting from the sun's surface. He was one of the first people to directly observe a solar flare. About 17 hours later, the associated coronal mass ejection reached Earth, triggering the most powerful geomagnetic storm ever recorded. Telegraph systems around the world went haywire. Operators received electric shocks. Paper printouts caught fire. Some telegraph lines continued to operate even after their power sources were disconnected, powered solely by the electric currents induced by the geomagnetic storm. Auroras appeared across the globe, visible from the tropics to the poles. Gold miners in the Rocky Mountains woke in the middle of the night, convinced it was dawn because the sky was so bright. If an event like the Carrington event happened today, the consequences would be far more severe. In 1859, human technology was relatively primitive. Telegraph systems were the most advanced electrical infrastructure of the time, and while they were disrupted, society didn't depend on them for survival. Today, we rely on electrical grids, satellites, GPS, internet, telecommunications, all vulnerable to geomagnetic storms. A Carrington-level event in the modern era could cause trillions of dollars in damage. Power grids could fail across entire continents. Transformers, the large devices that step electrical voltage up and down, could be permanently damaged by the induced currents, taking months or years to replace. Satellites could be disabled or destroyed. GPS signals could become unreliable or unavailable. Communication networks could go down. The cascading effects could disrupt everything from food distribution to medical care to financial systems. Scientists estimate that the probability of a Carrington-level storm happening in any given decade is about 10 to 12%. That might not sound high, but over the course of a century, it becomes almost certain. We will experience another major solar storm. The question is when and whether we'll be prepared. Some countries have begun taking steps to protect critical infrastructure. Utilities are installing devices to monitor geomagnetic activity and disconnect vulnerable transformers before they're damaged. Space agencies are launching satellites to monitor the sun and provide early warning of incoming CMEs. But much more needs to be done. The challenge is that preparing for rare but catastrophic events requires investment and planning, and it's hard to prioritize those efforts when the event might not happen for decades. The sun goes through an 11-year cycle of activity, from solar minimum, when the sun is relatively quiet with few sunspots, to solar maximum, when the sun is active with many sunspots and frequent eruptions. We're currently approaching the next solar maximum, expected around 2025. During solar maximum, the risk of major solar storms increases. This doesn't mean a catastrophic storm is guaranteed, but the odds are higher. Solar physicists are watching the sun closely, tracking sunspot development, monitoring flares and CMEs, trying to predict which eruptions might be Earth-directed. It's not an exact science. The sun is chaotic, and forecasting space weather is as challenging as forecasting terrestrial weather. Perhaps more so. But let's return to the auroras, because they're the most beautiful manifestation of the interaction between the sun and Earth's magnetic field. When solar particles funnel down along the magnetic field lines and collide with atmospheric gases, they transfer energy to those gases. Oxygen and nitrogen atoms become excited, meaning their electrons jump to higher energy levels. When the electrons fall back to their normal levels, they release the excess energy as light. The color of the light depends on which gas is involved and at what altitude the collision occurs. Oxygen at high altitudes, above 150 miles, produces red auroras. Oxygen at lower altitudes, around 60 to 150 miles, produces green, the most common auroral color. Nitrogen produces blue or purple hues. The result is a shimmering curtain of light, constantly shifting and flowing as the particles rain down and the magnetic field fluctuates. Indigenous peoples in the far north have lived with the auroras for thousands of years, and many cultures developed myths and legends to explain them. Some believed the lights were the spirits of ancestors dancing in the sky. Others thought they were reflections of campfires from distant lands or torches carried by sky beings. The Sami people of Scandinavia believed the lights were caused by a magical fox running across the snow, its tail sweeping up snowflakes that sparkled in the moonlight. In Norse mythology, the auroras were thought to be the Bifrost, the rainbow bridge connecting Earth to Asgard, the realm of the gods. These stories reflect a deep human need to make sense of mysterious natural phenomena, to weave them into the fabric of culture and belief. Today, we know the scientific explanation, but that doesn't diminish the wonder. If anything, understanding the auroras makes them more impressive. You're watching solar particles that traveled 93 million miles through space, particles that were accelerated by magnetic reconnection in Earth's magnetotail, particles that survived the journey through the magnetosphere and are now colliding with the atmosphere at altitudes of 60 to 200 miles above the ground, releasing energy as visible light. You're witnessing the interaction of the sun and Earth, a cosmic dance that's been happening for billions of years. The auroras are proof that we live in a dynamic universe, where planets and stars influence each other across vast distances, where invisible forces shape the conditions for life. There's another phenomenon related to the auroras that fewer people know about. It's called STEVE, which stands for Strong Thermal Emission Velocity Enhancement. STEVE appears as a narrow ribbon of purple or mauve light stretching across the sky, often accompanied by green vertical structures that look like a picket fence. For years, aurora enthusiasts photographed Steve, but scientists weren't sure what it was. It didn't quite fit the pattern of normal auroras. Recent research suggests Steve is caused by a different mechanism, a fast-flowing river of extremely hot plasma at high altitudes, around 280 miles up, moving at speeds of 13,000 miles per hour. The picket fence structures are caused by particles accelerating along magnetic field lines. Steve is rarer than regular auroras and typically appears at slightly lower latitudes. It's a reminder that even phenomena we thought we understood, like auroras, still hold surprises. Auroras don't just occur on Earth. Any planet with a magnetic field and an atmosphere can have them. Jupiter has spectacular auroras, powered not just by the solar wind but also by particles from its volcanic moon Io. Saturn has auroras too, sometimes triggered by solar storms, other times by interactions with its moons. Mars, which lacks a global magnetic field, doesn't have planet-wide auroras, but it does have localized auroral events in regions where ancient crustal magnetic fields remain. Even some moons show auroral activity. Ganymede, one of Jupiter's moons and the only moon in the solar system with its own magnetic field, has faint auroras. These aurora across the solar system tell us that the interaction between magnetic fields and charged particles is universal, a fundamental process playing out on many worlds. Can you imagine what it would be like to stand on Jupiter and watch its auroras? They'd be far more intense than anything on Earth. Enormous ovals of light surrounding the magnetic poles, flickering and dancing as particles from Io and the solar winds spiral down. Or picture yourself on a planet orbiting a star more active than our Sun, where solar storms are frequent and powerful, where the sky is almost always lit with auroras, where the magnetic field is constantly battling to protect the planet from the relentless assault of stellar radiation. Earth's auroras are beautiful, but they're relatively gentle. We're lucky to orbit a star that's stable and calm most of the time. Still, even our calm sun can surprise us. In 2012, a powerful CME erupted from the sun and missed Earth by just a few days. If it had happened a week earlier, when Earth was in that part of its orbit, it would have hit us directly. Analysis suggested it was comparable in strength to the Carrington event. We got lucky. The storm passed through Earth's orbit, but we weren't there. It hit a NASA satellite instead, which measured the intensity and confirmed just how powerful it was. That near miss was a wake-up call. It demonstrated that we're one unlucky week away from a technological catastrophe. Space weather is not a distant, abstract threat. It's real, it's unpredictable, and we need to take it seriously. The magnetic field, the magnetosphere, the auroras, the solar storms, all of these pieces fit together into a single story. The story of a planet protected by an invisible shield, a shield generated deep within the Earth and extending far into space, a shield constantly tested by the sun's restless energy. Most of the time, the shield holds. Most of the time, we're safe. But the balance is delicate, maintained by forces we're still learning to understand, and as we've seen, the shield itself can change, weaken, reverse, or even fail. The magnetic field is not a guarantee. It's a gift, a consequence of Earth's size, composition, and internal heat. A gift that won't last forever, but will last long enough, we hope, for life to continue, for civilizations to rise and fall, for humanity to reach for the stars. So here's something to think about as you drift towards sleep. Right now, above your head, the solar wind is blowing past Earth at 1,000,000 miles per hour. The magnetosphere is deflecting it, shaping it, channeling particles toward the poles. The auroras might be dancing over the Arctic and Antarctic, glowing green and red and purple against the darkness. And deep below your feet, molten iron is churning, generating the magnetic field that makes all of this possible. You're part of this system, a small piece of a planetary-scale process that connects the core to the cosmos. Does that make you feel small, or does it make you feel connected to something vast and ancient? The solar wind isn't the only threat from space. Beyond our solar system, from the farthest reaches of the galaxy and beyond, particles are constantly raining down on Earth. These are cosmic rays, high-energy particles traveling at nearly the speed of light, and they come from some of the most violent events in the universe. Let's talk about where cosmic rays come from. Despite the name, they're not rays of light. They're particles, mostly protons, the nuclei of hydrogen atoms, but also heavier atomic nuclei and even electrons. They're called rays because when scientists first detected them in the early 20th century, they behaved like radiation, penetrating matter and ionizing atoms. It took decades to figure out what they actually were. The lower energy cosmic rays come from our sun, ejected during solar flares and other eruptions. But the truly high-energy cosmic rays, the ones traveling at 99.9% the speed of light or faster, come from outside the solar system. They're born in supernova explosions, the deaths of massive stars. When a star many times larger than our sun runs out of fuel, its core collapses in a fraction of a second, and the outer layers explode outward with unimaginable force. The explosion releases more energy in a few seconds than the sun will emit in its entire 10 billion-year lifetime. In that cataclysm, particles are accelerated to incredible speeds, flung into space as cosmic rays. Some cosmic rays come from even more exotic sources. Pulsars, rapidly spinning neutron stars left behind after supernovae, can accelerate particles. Active galactic nuclei, supermassive black holes at the centers of galaxies devouring matter and spewing out jets of energy, produce cosmic rays. Gamma-ray bursts, the most powerful explosions in the universe, might contribute as well. These particles travel across the galaxy for thousands or millions of years, scattered by magnetic fields, deflected by interstellar clouds, until finally, by chance, they encounter Earth. When a high-energy cosmic ray enters Earth's atmosphere, it collides with an air molecule, shattering it and creating a cascade of secondary particles. This shower of particles spreads out as it descends, and by the time it reaches the ground, it might cover an area the size of a football field. Detectors can measure these showers, allowing scientists to study cosmic rays, even though the original particle was destroyed high in the atmosphere. Cosmic rays pose a radiation hazard, especially at high altitudes where the atmosphere is thinner and provides less shielding. Airline crews and frequent flyers receive higher radiation doses than people who stay on the ground. Astronauts in space, outside the protection of Earth's atmosphere and magnetic field, are exposed to much higher levels. On a mission to Mars, which could take 6 to 9 months each way, astronauts would accumulate radiation doses that increase their lifetime cancer risk. This is one of the major challenges for deep space exploration. We can shield spacecraft to some extent, but cosmic rays are so energetic that they can penetrate many materials. Some particles can even pass through several feet of lead. The only truly effective shielding would be extremely thick and heavy, impractical for space missions. But here on Earth's surface, we're protected. The atmosphere absorbs most cosmic rays, and the magnetic field deflects many of them before they even reach the atmosphere. Remember, cosmic rays are charged particles, and charged particles are influenced by magnetic fields. As a cosmic ray approaches Earth, the magnetic field bends its trajectory. Lower energy cosmic rays are deflected more strongly and might be turned away entirely, sent spiraling back into space. Higher energy cosmic rays are deflected less, but even a small deflection can be enough to prevent them from hitting densely populated areas. The magnetic field acts like a filter, allowing some cosmic rays through, particularly at the poles where the field lines converge, but blocking many others. Without the magnetic field, the cosmic ray flux reaching Earth's surface would be much higher, potentially damaging DNA, increasing mutation rates, and making the surface more hostile to complex life. There's an interesting connection between cosmic rays and climate that scientists have been investigating. When cosmic rays enter the atmosphere and create particle showers, they ionize air molecules, knocking electrons free. These ions can act as nucleation sites for water vapor, tiny seeds around which water droplets form. This could potentially influence cloud formation. More cosmic rays might mean more clouds, which would reflect more sunlight back into space, cooling the planet. Fewer cosmic rays might mean fewer clouds and a warmer planet. The sun's magnetic field, which varies over the 11-year solar cycle, affects how many cosmic rays reach Earth. During solar maximum, when the sun's magnetic field is stronger and more complex, it deflects more cosmic rays, so fewer reach Earth. During solar minimum, the sun's field is weaker and more cosmic rays get through. Some researchers have suggested that this cosmic ray cloud connection could be a factor in climate variation, though the effect is still debated and likely small compared to other climate drivers like greenhouse gases and ocean currents. What's fascinating is that Earth's magnetic field, by modulating cosmic ray exposure, might have influenced the evolution of life. Higher cosmic ray exposure means higher mutation rates. Mutations are the raw material for evolution, the genetic variations that natural selection acts upon. Too few mutations and evolution proceeds slowly. Too many mutations and the damage overwhelms the organism's ability to repair DNA, leading to cell death or cancer. There might be an optimal mutation rate, one that allows evolution to proceed efficiently without causing excessive harm. Earth's magnetic field, by shielding us, they've never been shown the route. The magnetic field provides a kind of map, a coordinate system that's imprinted in their genes. Sea turtles have an even more remarkable ability. Hatchlings emerge from eggs buried in beach sand and immediately crawl toward the ocean. Once in the water, they swim out to sea, guided by the magnetic field. As they mature, they roam across thousands of miles of open ocean, and then, years later, they return to the same beach where they were born to lay their own eggs. How do they find their way back? They appear to have a magnetic map in their brains, a memory of the magnetic field signature at their birth location. Even though the magnetic field changes slowly over time, turtles can compensate, adjusting their navigation to account for the drift. This ability is so finely tuned that even slight variations in the magnetic field can guide them to within a few miles of their target beach. Scientists are still trying to understand exactly how these animals sense the magnetic field. There are several theories. One involves magnetite crystals in the animals' bodies, tiny magnets that can physically rotate or vibrate in response to the external field, stimulating nerve cells. Another theory involves a quantum mechanical process in the eye, where certain light-sensitive proteins are affected by the magnetic field, altering the chemical reactions that produce vision. This second mechanism, called the radical pair mechanism, is extraordinarily sensitive and might allow animals to literally see the magnetic field as patterns of light or darkness overlaid on their normal vision. Imagine being able to see invisible lines of force curving through the sky and ground, always knowing which way is north without having to think about it. That's what these animals experience every day. But here's the troubling part. If the magnetic field reverses, or even just weakens significantly, what happens to these animals? Their navigation systems are calibrated to the current field. If the field changes, they might become disoriented. Migration routes could be disrupted. Sea turtles might fail to find their breeding beaches. Birds might fly in the wrong direction and end up in unsuitable habitats. Salmon might not find their way back to their spawning streams. This could cause population declines, especially for species that already face threats from habitat loss, pollution, and climate change. During past magnetic reversals, did animal populations suffer? It's hard to say. The fossil record doesn't preserve behavior, so we can't directly observe how ancient animals responded to changing magnetic fields. But if reversals happen slowly enough, perhaps taking thousands of years, animals might have time to adapt, either through learning or through evolutionary changes to their magnetic sensing organs. Humans, on the other hand, don't have a natural magnetic sense. Or do we? Some recent studies have suggested that humans might have a vestigial ability to detect magnetic fields, one we're not consciously aware of. Researchers placed people in controlled environments and exposed them to rotating magnetic fields while measuring their brain activity. They found that certain brainwave patterns changed in response to the magnetic field, suggesting that some part of the human brain is reacting to it, even though the person doesn't consciously perceive anything. This doesn't mean we can navigate by the magnetic field the way birds do, but it hints that deep in our evolutionary past, our ancestors might have had that ability, and traces of it remain in our nervous system. It's a humbling thought. We pride ourselves on our technology, our compasses, and GPS systems, but birds navigate across continents using senses we've lost or never fully developed. Now, let's come back to the idea of the magnetic field as a shield. But think about it in broader terms. The magnetic field protects us from the solar wind. It protects us from cosmic rays, but it also protects the atmosphere itself from being eroded away. Mars is a cautionary tale in this regard. Mars is smaller than Earth, so it cooled faster. Its core solidified, or at least the geodynamo shut down, billions of years ago. Without a magnetic field, the solar wind began stripping away Mars's atmosphere. Over hundreds of millions of years, the thick atmosphere that Mars once had, an atmosphere that might have supported liquid water on the surface, was eroded particle by particle until only a thin remnant remained. Today, Mars's atmosphere is about 1% as thick as Earth's. The surface is cold, dry, and bathed in radiation. Any water that might still exist is locked underground as ice. The planet is essentially dead, geologically and biologically. Earth could have suffered the same fate. If Earth's core had solidified early in its history, if the geodynamo had shut down before life evolved, the solar wind would have stripped away our atmosphere. The oceans would have evaporated, the water molecules broken apart by solar radiation, hydrogen escaping into space, oxygen reacting with rocks. Earth would be a barren world, perhaps with a thin atmosphere of carbon dioxide like Mars, but nothing more. Life as we know it would never have emerged. But Earth's core didn't solidify. The geodynamo kept running, the magnetic field kept protecting the atmosphere, and life had a chance. 4 billion years ago, simple cells appeared in Earth's oceans. Over time, they evolved into more complex forms, eventually colonizing the land, filling the skies, creating the rich biosphere we see today. And through all of that time, the magnetic field was there, silently working, deflecting the solar wind, blocking cosmic rays, preserving the conditions that made it all possible. Think about the fragility of this. Life on Earth depends on so many factors aligning just right. The right distance from the sun, the right size planet to retain an atmosphere but not so large that gravity crushes everything, the right chemical composition to allow a geodynamo to operate, the right amount of internal heat to keep the outer core molten for billions of years. If any one of these factors had been different, Earth might be lifeless. And yet, here we are. Against the odds, life emerged, evolved, became conscious, and now sits here contemplating its own existence and the forces that made it possible. There's something almost miraculous about it, though it's not a miracle in the supernatural sense. It's a consequence of physics, chemistry, and probability. Given enough planets, enough time, the right conditions will eventually occur somewhere. We happen to be on one of those somewheres. The magnetic field also connects us to the deep past. The iron in your blood, the iron that makes your blood red, was forged in the core of a massive star billions of years ago. That star exploded in a supernova, scattering its iron across space. Some of that iron eventually coalesced into the cloud of gas and dust that formed our solar system. Some of it ended up in Earth's core, where it now flows as liquid metal, generating the magnetic field. And some of it ended up in your body, carrying oxygen through your bloodstream. You are made of stardust, quite literally. The atoms in your body are billions of years old, recycled from previous generations of stars. And those same atoms, in the form of molten iron thousands of miles below you, are protecting you right now from the dangers of space. You're part of a cosmic cycle, connected to the stars. to the core of the Earth, to the solar wind, to the magnetic field. Everything is linked. As you lie there, drifting toward sleep, can you feel that connection? You're not separate from the universe. You're a piece of it, a small but integral part of a vast, interconnected system. The magnetic field is your shield, generated by processes you'll never witness, protecting you from threats you'll never see. The sun is your source of energy, warming the planet, driving the weather, making photosynthesis possible. The atmosphere is your blanket, holding in warmth, filtering out harmful radiation, giving you air to breathe. And deep within the Earth, ancient heat is still radiating outward, sustaining the geodynamo, keeping the magnetic field alive. All of these systems work together, and you exist because they do. If you were to ask what the most important discovery in the history of science is, you'd get many different answers. The structure of DNA, the theory of evolution, the laws of thermodynamics, quantum mechanics, general relativity. All of these are profound insights into how the universe works. But I would argue that understanding Earth's magnetic field, understanding what generates it, how it protects us, and what would happen without it, is equally important. Because without the magnetic field, none of the other discoveries would matter. There would be no life to evolve, no DNA to study, no humans. How do you study something you can't see? How do you measure an invisible force that extends thousands of miles into space and thousands of miles into the Earth? For centuries, scientists struggled with these questions. But slowly, through careful observation and clever instruments, they learned to see the unseeable. The story begins with a simple device, the compass, a magnetized needle, free to rotate, that always points north. For hundreds of years, that was the only tool humans had for detecting Earth's magnetic field. But even that simple tool revealed important patterns. Sailors noticed that the compass didn't always point exactly toward the geographic North Pole. There was a difference, an angle between magnetic north and true north. This angle, called magnetic declination, varies depending on where you are on Earth. In some places, the compass points east of true north. In other places, it points west. Early navigators had to account for this when plotting their courses, adjusting their compass readings based on tables of declination values for different locations. In 1831, British scientist James Clark Ross located the North Magnetic Pole in the Canadian Arctic, an incredible feat of exploration and navigation. He measured the magnetic field at that location and found that the needle of a compass, when allowed to pivot vertically as well as horizontally, pointed straight down. This made sense. At the magnetic pole, the field lines are vertical, entering or exiting the Earth perpendicularly. Stand at the North Magnetic Pole with a compass, and the needle doesn't point north or south or anywhere horizontal. It points down, into the ground. Ross's expedition confirmed what scientists had theorized. Earth had magnetic poles distinct from its geographic poles, and those magnetic poles were where the field lines converged. But measuring the field at a few locations wasn't enough. Scientists needed a global picture. They needed to map the field everywhere, understand how it changed over time, and figure out what was causing it. This required a new kind of instrument. In the mid-19th century, researchers developed magnetometers, devices that could measure not just the direction of the magnetic field, but also its strength. Early magnetometers were delicate, sensitive instruments that had to be carefully shielded from external magnetic influences. They were placed in dedicated observatories, special buildings constructed without iron or steel, which would distort the measurements. These observatories were located around the world, from remote Arctic stations to tropical islands, each one contributing data to the growing map of Earth's magnetic field. Over decades, scientists compiled measurements from hundreds of locations. Patterns emerged. The magnetic field was strongest near the poles and weakest near the equator. The field wasn't perfectly aligned with Earth's rotation axis. It tilted at an angle, about 11 degrees off, and most intriguingly, the field was changing. Not just in small, random fluctuations, but in systematic ways. The magnetic poles were drifting. The strength of the field was varying. Some regions were getting stronger, others weaker. The magnetic field was alive, dynamic, responding to processes deep within the Earth that no one yet understood. It wasn't until the 20th century that scientists developed a theory to explain the magnetic field. The geodynamo theory, which we discussed earlier, proposed that the field was generated by the motion of molten iron in the outer core. But confirming this theory required understanding what the core was actually made of. No one had ever drilled more than a few miles into the Earth's crust, and the core was thousands of miles down. How could anyone know what was there? The answer came from an unexpected source: earthquakes. When an earthquake occurs, it generates seismic waves that travel through the Earth. These waves behave differently depending on what material they pass through. Some waves can travel through solid rock, but not through liquid. Others travel through both, but at different speeds. By placing seismometers around the world and measuring how long it took seismic waves from earthquakes to reach different locations, scientists could infer the structure of Earth's interior. They discovered that Earth had layers: a solid crust, a thick, partially molten mantle, a liquid outer core, and a solid inner core. This was extraordinary. Without ever visiting the core, without ever drilling down to see it, scientists had mapped its structure using nothing but the echoes of earthquakes. And the presence of a liquid outer core made perfect sense for the geodynamo theory. Liquid iron, constantly in motion, was exactly what you'd need to generate a magnetic field. The discovery of the inner core, the solid iron center, came even later, in 1936, when Danish seismologist Inge Lehmann analyzed seismic data and realized there had to be another boundary deep within the core where the properties changed. She was right. The inner core was solid, crystallized under immense pressure, and it was growing slowly as the Earth cooled and more iron solidified. With the structure of the core understood, scientists could refine the geodynamo theory. They could build mathematical models, run computer simulations, and test their predictions against observations. And slowly, the picture came into focus. The magnetic field was indeed generated by convection in the outer core, driven by heat and influenced by Earth's rotation. The models even reproduced magnetic reversals, confirming that reversals were a natural consequence of the geodynamo's chaotic behavior. But there was still so much to learn. The models were simplified. The real core was far more complex, with turbulent flows, temperature gradients, chemical variations, and interactions between the inner and outer core that weren't fully understood. Even today, with supercomputers and advanced mathematics, we can't predict exactly when the next reversal will occur or precisely how the magnetic field will change in the coming decades. This is where satellites come in. In the 1960s and 70s, scientists began launching satellites equipped with magnetometers into orbit around Earth. These satellites could measure the magnetic field from above the atmosphere, free from the distortions caused by local magnetic anomalies on the ground. They provided a global view, mapping the entire magnetic field in unprecedented detail. One of the most important of these missions was MagSat, launched by NASA in 1979. MagSat orbited Earth for just 6 months before re-entering the atmosphere and burning up. But in that short time, it collected invaluable data, creating the most detailed map of Earth's magnetic field to date. The data revealed the fine structure of the field, including crustal magnetic anomalies, regions where ancient rocks retained magnetic signatures from millions of years ago. Then came the Ørsted satellite, launched by Denmark in 1999. Followed by the German CHAMP satellite in 2000. These missions extended the record, tracking how the magnetic field changed over years and decades. And in 2013, the European Space Agency launched SWARM, a constellation of 3 satellites flying in formation, measuring the magnetic field from different altitudes simultaneously. SWARM's data has been transformative. It's revealed rapid changes in the magnetic field that scientists didn't know were possible, sudden shifts in the flow of molten iron in the outer core that occur over just a few years. These changes, the geomagnetic jerks I mentioned earlier, are evidence that the core is far more dynamic than anyone expected. The outer core isn't just slowly convecting. It's churning, accelerating, decelerating, shifting in ways that affect the magnetic field on human timescales. SWARM has also provided new insights into the South Atlantic anomaly. This weak spot in the magnetic field over the South Atlantic has been growing and intensifying. SWARM's data shows that the anomaly is actually splitting into two separate weak regions, one over South America and one over the southern Atlantic Ocean. Scientists aren't sure what this means. Is it the beginning of a magnetic reversal? Is it just a normal fluctuation that will eventually correct itself? The data isn't clear yet, but SWARM is watching, measuring, recording every shift and change, building a database that future scientists will use to understand the magnetic field's long-term behavior. What's remarkable is that we can now monitor the magnetic field in real time. There are ground-based observatories on every continent, satellites in orbit measuring the field from above, and even ocean buoys equipped with magnetometers tracking the field over the seas. All of this data flows into central databases where scientists can access it, analyze it, and look for patterns. It's a global effort, a collaboration between countries and institutions, all working together to understand this fundamental property of our planet. And the data is publicly available. Anyone with an internet connection can download magnetic field measurements from around the world, plot them, analyze them, and contribute to our collective understanding. That's the beauty of modern science. It's open, collaborative, and built on shared knowledge. But studying the magnetic field isn't just about understanding Earth. It's also about understanding other planets. When spacecraft visit Mars, Venus, Mercury, or the moons of Jupiter and Saturn, they carry magnetometers to measure magnetic fields at those locations. What they've found is fascinating. Every planet and moon has a different magnetic story. Mars, as I mentioned, has no global magnetic field, but it does have localized crustal magnetic fields, remnants of a time when the planet had an active geodynamo. These crustal fields are strongest in the ancient southern highlands, suggesting that Mars's magnetic field shut down early in its history, before the northern lowlands formed. Why did Mars's field die? Probably because the planet is smaller and cooled faster, but the exact mechanism is still debated. Venus has no magnetic field at all, or at most a very weak one. Its slow rotation might prevent the formation of a geodynamo. Mercury, despite being even smaller than Mars, has a weak but definite magnetic field, which is puzzling. Some scientists think Mercury's core might still have a liquid layer, kept molten by tidal heating from the sun's gravity. Others suggest the field might be a remnant, frozen into the planet from an earlier time when it had a more active core. The moons of Jupiter, particularly Ganymede, are even more interesting. Ganymede is the only moon in the solar system with its own magnetic field, generated by a liquid iron core kept warm by tidal heating from Jupiter's immense gravity. This makes Ganymede unique, a moon with some of the properties we'd expect from a planet. What all of this tells us is that magnetic fields are not rare in the solar system. Many bodies have them or had them at some point in their history. But sustained, long-lived magnetic fields like Earth's are special. They require the right combination of size, composition, and internal heat to maintain a geodynamo for billions of years. Most planets and moons don't have that. Earth does. And that makes all the difference. Now, let's imagine something audacious. What if we wanted to give Mars back its magnetic field? What if we tried to terraform Mars, not just by adding atmosphere and warming the planet, but by creating an artificial magnetic shield to protect that atmosphere from being stripped away by the solar wind? Is such a thing even possible? The challenge is immense. Mars's core is likely solid or mostly solid. We can't restart a geodynamo that's been dead for billions of years. Even if we could somehow heat the core enough to melt it, again, We have no way to do that with current or foreseeable technology. You'd need to inject enormous amounts of energy into the planet's interior, energy on a scale that dwarfs anything humanity has ever produced. It's not practical. But there's another approach, one that might be within the realm of possibility in the distant future. You could create an artificial magnetic field using technology rather than relying on a natural geodynamo. Here's one proposal that scientists have seriously considered. You could place a massive superconducting magnet in orbit between Mars and the Sun, at a point called the L1 Lagrange point, where the gravitational pull of Mars and the Sun balance. This magnet would generate a magnetic field strong enough to deflect the solar wind before it reaches Mars. The artificial field wouldn't need to be as strong as Earth's natural field because it would be positioned farther out, intercepting the solar wind before it got close to the planet. If the solar wind were deflected, Mars's atmosphere would no longer be eroded. Over millions of years, volcanic outgassing and comet impacts could gradually rebuild the atmosphere. The planet could warm. Water ice could melt. Mars might become habitable again. This isn't science fiction. Well, it is, but it's science fiction based on real physics. A study by NASA scientists in 2017 explored this concept and concluded that it was theoretically feasible. The magnet would need to be enormous, generating a field with a strength of about 1 to 2 Tesla. Much stronger than a typical refrigerator magnet, but within the range of what superconducting magnets can produce today. The challenge would be building it, launching it, positioning it at the L1 point, and keeping it powered. You'd need a massive energy source, probably nuclear, and you'd need to maintain the system for centuries or millennia to allow Mars's atmosphere to rebuild. It's a multi-generational project, something that would require sustained commitment and resources on a scale humanity has never attempted. But it's not impossible. It's the kind of thing an advanced spacefaring civilization could do if it chose to. And this raises an interesting question. If we can imagine creating an artificial magnetic field for Mars, could an alien civilization do the same for their own planet? Could there be worlds out there that were once uninhabitable, dead rocks with no magnetic fields, that were transformed by advanced technology into thriving homes for life? We don't know. We've never detected any evidence of such megastructures around other stars, but our ability to detect them is limited. If an artificial magnetic field generator existed around a planet orbiting a distant star, we probably couldn't see it with current telescopes. It's entirely possible that some of the exoplanets we've discovered, planets orbiting other stars, are protected by artificial magnetic fields created by civilizations far older and more advanced than ours. Let's talk about the future. Not the distant future when the sun dies or Earth's core solidifies, but the near future, the next few decades, the next century. What will happen to Earth's magnetic field during your lifetime, during your children's lifetimes, during the lifetimes of the next few generations? The honest answer is that we don't know for certain. The magnetic field is changing. That much is clear from the data. The question is whether those changes are leading toward something dramatic, like a reversal, or whether they're just normal fluctuations that will eventually settle down. Scientists are divided on this. Some look at the weakening field strength, particularly over the South Atlantic anomaly, and see warning signs. The field has lost about 9% of its strength globally over the past 200 years. In some regions, the loss has been even steeper. The South Atlantic anomaly has weakened by more than 30% in the same period. These are significant changes, happening quickly by geological standards. If the trend continues, the field could weaken to the point where its protective abilities are compromised, at least temporarily. Other scientists are more cautious. They point out that we've only been measuring the magnetic field with precision for a few hundred years. That's a tiny snapshot of geological time. The field might naturally fluctuate by 10 or 20% over centuries without any long-term consequences. We might be seeing a temporary dip, one that will correct itself in a few hundred years. Without a longer baseline of data, it's hard to say. The geological record, the magnetic signatures locked in ancient rocks, suggests that the field's strength has varied considerably over millions of years. But the time resolution in that record isn't fine enough to see changes happening over decades or centuries. We're essentially flying blind, trying to predict the behavior of a chaotic system with limited data. What we can say is that the magnetic poles are definitely moving. The North Magnetic Pole has been drifting from the Canadian Arctic toward Siberia at an accelerating rate. In the early 20th century, it was moving about 10 miles per year. By the 1990s, it had accelerated to about 34 miles per year. Recent measurements show it's now moving even faster, covering 30 to 40 miles annually. At this rate, the North Magnetic Pole could be in Siberia within a few decades. The South Magnetic Pole is also drifting, though more slowly, wandering across the Southern Ocean off the coast of Antarctica. This movement isn't unusual. The poles have always drifted, but the acceleration is notable. It suggests that something in the core, some change in the flow patterns of molten iron, is driving the poles to move faster than they have in recent history. Does this mean a reversal is coming? Possibly, but not necessarily. Pole movement and field weakening can happen without a full reversal. The field might weaken for a while, the poles might wander, and then the system could stabilize again without flipping. Or the weakening could continue. The field could become chaotic with multiple poles appearing, and eventually, the polarity could reverse. We won't know until it happens. And even if a reversal does begin in the next century or two, it would unfold over thousands of years, slowly enough that each generation would experience only a small part of the transition. The implications for technology, though, are worth considering. Even a modest weakening of the field increases our vulnerability to space weather. A solar storm that would have been manageable with a full-strength magnetic field could cause more damage if the field is weakened. Satellites in low Earth orbit, particularly those passing through the South Atlantic anomaly, already experience higher radiation levels. As the anomaly grows, more satellites will be affected. This means more frequent malfunctions, shorter operational lifetimes, and higher costs for space infrastructure. Communication satellites, GPS satellites, Earth observation satellites, all of them are at risk. And as our civilization becomes more dependent on space-based technology, any disruption becomes more consequential. There's also the question of astronauts. As we expand human presence in space, sending missions to the Moon, Mars, and beyond, radiation exposure becomes a critical concern. Astronauts on the International Space Station are protected to some extent by being inside the magnetosphere, though even there, they receive higher radiation doses than people on the ground. During spacewalks, especially over the South Atlantic anomaly, radiation levels can spike. Astronauts are instructed to avoid spacewalks when the station is passing through that region if possible. But on missions to the Moon or Mars, there's no magnetosphere for protection. Astronauts would be exposed to the full force of the solar wind and cosmic rays. A major solar storm during a lunar or Martian mission could deliver a dangerous, potentially lethal radiation dose. This is one of the biggest challenges for deep space exploration, and it's one we haven't fully solved yet. Some proposals involve building shielded habitats on the Moon or Mars, underground bases where the rock overhead absorbs radiation. Others suggest using water or other materials as shielding around spacecraft and habitats. Water is particularly effective because hydrogen atoms are good at absorbing high-energy particles. A few feet of water surrounding a spacecraft could significantly reduce radiation exposure. But water is heavy, and launching heavy payloads into space is expensive. There are no easy solutions. We'll need to be creative, combining multiple strategies to protect astronauts on long-duration missions. Another possibility is developing better medical countermeasures. Radiation damages DNA, increasing the risk of cancer and other health problems. But cells have repair mechanisms, ways of fixing damaged DNA before it causes mutations. If we could enhance those repair mechanisms, perhaps through drugs or gene therapy, we could make humans more resistant to radiation. This is still in the realm of research, but it's an active area of study. Some organisms on Earth, like the bacterium Deinococcus radiodurans, can survive radiation levels that would kill a human almost instantly. They have incredibly efficient DNA repair systems. If we could understand how those systems work and apply that knowledge to human medicine, we might be able to protect astronauts and even people on Earth who are exposed to high radiation levels due to medical treatments or accidents. But let's return to Earth and think about what the weakening magnetic field means for people living here, on the surface, under the protection of the atmosphere. For most people, the answer is not much. The atmosphere will continue to absorb the vast majority of incoming radiation, even if the magnetic field weakens significantly. You're not going to suddenly start getting sunburned from cosmic rays. The ozone layer, which filters out harmful ultraviolet light from the sun, will continue to do its job. Life on the surface will carry on largely as it has for billions of years. The real risks are to technology, satellites, power grids, communication systems, and to people in high-altitude environments, like airline crews, or in space, like astronauts. There is, however, one intriguing possibility that scientists have considered. If the magnetic field weakens enough, the upper atmosphere could be exposed to more solar wind particles. This could change the chemistry of the atmosphere at high altitudes, affecting the ozone layer. Some models suggest that during a magnetic reversal, when the field is at its weakest, ozone depletion could increase, allowing more ultraviolet radiation to reach the surface. This wouldn't be catastrophic, but it could have subtle effects on ecosystems, particularly on organisms sensitive to UV light. Marine plankton, for instance, live near the ocean's surface and are vulnerable to UV damage. If UV levels increased, plankton populations could decline, which would have cascading effects through the food chain. Again, this is speculative. We don't have direct evidence of widespread ecological damage during past reversals, but the possibility is worth considering. Now, let's shift our focus outward, beyond Earth, and think about what the magnetic field tells us about the search for life on other worlds. Over the past few decades, astronomers have discovered thousands of planets orbiting other stars. These exoplanets come in all sizes, from gas giants larger than Jupiter to rocky worlds smaller than Earth. Some orbit close to their stars, baked by intense heat. Others orbit farther out, cold and distant. And a few, just a few, orbit in the habitable zone, the region around a star where temperatures are just right for liquid water to exist on the surface. The habitable zone is a useful concept, but it's not the whole story. Being in the habitable zone is necessary for life as we know it, but it's not sufficient. A planet could be in the habitable zone and still be uninhabitable if it lacks an atmosphere, or if its atmosphere is too thick and creates a runaway greenhouse effect like Venus, or if it has no magnetic field to protect that atmosphere from erosion. Earth is habitable not just because it's the right distance from the sun, but because it has the right size, the right composition, the right amount of water, and yes, the right magnetic field. All of these factors work together. So when astronomers search for potentially habitable exoplanets, they're starting to consider magnetic fields as one of the criteria. The problem is, detecting a magnetic field on a planet orbiting another star is incredibly difficult. We can't send a spacecraft there to measure it directly. We can't even see most exoplanets directly. They're too small and too faint, lost in the glare of their parent stars. We infer their existence by observing the star. If a planet passes in front of the star from our point of view, it blocks a tiny fraction of the star's light, and we can detect that dimming. Or we can measure the star's wobble, the gravitational tug of the planet as it orbits, which causes the star to move slightly back and forth. These methods tell us a planet exists, its size, its mass, and its orbital distance, but they don't tell us if it has a magnetic field. There are some indirect clues, though. If a planet has a magnetic field, it will have a magnetosphere, and that magnetosphere will interact with the stellar wind, the equivalent of the solar wind coming from the planet's star. This interaction could produce radio emissions, similar to the auroral radio emissions that Jupiter produces. Jupiter's auroras emit powerful radio waves that can be detected from Earth. If an exoplanet had a strong magnetic field and intense auroras, we might be able to detect those radio emissions with radio telescopes. Some astronomers are searching for exactly this, scanning nearby stars for radio signals that could indicate the presence of magnetospheres around orbiting planets. So far, no definitive detections have been made, but the technology is improving. In the coming decades, we might start finding exoplanets with detectable magnetic fields. Another approach is to look at the star itself. Some stars are more active than others, producing more frequent and more powerful stellar flares and coronal mass ejections. If a planet orbits a very active star, it's constantly being bombarded by high-energy particles. Without a magnetic field, the planet's atmosphere would be stripped away relatively quickly on timescales of hundreds of millions of years. So if we find a planet orbiting an active star, and that planet still has a thick atmosphere, it might be a sign that the planet has a magnetic field protecting it. This is indirect reasoning, but it's the best we can do with current technology. There's also the question of what kind of stars are most likely to host habitable planets with magnetic fields. Our Sun is a G-type star, medium-sized, stable, with a lifespan of about 10 billion years. But G-type stars are relatively rare. Most stars in the galaxy are smaller, cooler M-type stars, also called red dwarfs. Red dwarfs are much more common than Sun-like stars, and they have incredibly long lifespans, hundreds of billions of years. This makes them attractive targets in the search for life. A planet orbiting a red dwarf could potentially remain habitable for far longer than Earth will remain habitable around the Sun. But red dwarfs have a problem. They're highly variable, especially when they're young. They produce frequent, powerful flares that could strip away a planet's atmosphere. For a planet to remain habitable around a red dwarf, it would almost certainly need a strong magnetic field. And here's where it gets tricky. Planets close enough to a red dwarf to be in the habitable zone, where temperatures are right for liquid water, are also close enough to be tidally locked. Tidal locking is when a planet's rotation period matches its orbital period, so the same side of the planet always faces the star, like how the moon always shows the same face to Earth. Tidally locked planets might not rotate fast enough to generate a strong geodynamo. Remember, Earth's magnetic field depends in part on the planet's rotation, which drives the convection patterns in the outer core. If a planet rotates too slowly, the geodynamo might not work, or might produce a much weaker field. This doesn't mean tidally locked planets can't have magnetic fields. Venus rotates extremely slowly and still had a geodynamo early in its history, though it's unclear if it does now. And some models suggest that tidal heating, the flexing of a planet's interior caused by gravitational interactions with its star, could drive convection in the core even without fast rotation. But it's uncertain. We don't have examples to study. We've never observed a tidally locked exoplanet's magnetic field. This is one of the great unknowns in the search for habitable worlds. If tidally locked planets can't sustain magnetic fields, then most planets around red dwarfs might be uninhabitable, despite being in the right temperature zone. But if they can sustain fields through tidal heating or other mechanisms, then red dwarf systems might be teeming with life. It's a humbling reminder of how much we still don't know. We've discovered thousands of exoplanets, but we understand very little about their detailed properties. We don't know if they have atmospheres, oceans, magnetic fields, or any of the other features that make Earth habitable. We're like someone looking at distant lights through a heavy fog, able to see that something is there, but unable to make out the details. The next generation of telescopes, particularly the James Webb Space Telescope, and future missions like the Nancy Grace Roman Space Telescope and the Habitable Worlds Observatory, will help. They'll be able to analyze the atmospheres of some exoplanets, looking for gases like oxygen, methane, and water vapor that could indicate the presence of life. And maybe, just maybe, they'll find signs of magnetic fields too. The existence of Earth's magnetic field also raises a philosophical question. If magnetic fields are essential for life, and if magnetic fields require specific planetary conditions, large size, molten iron core, sufficient internal heat, fast rotation, then habitable planets might be rarer than we think. The habitable zone concept suggests that many stars could have planets in the right temperature range. But if you add the requirement for a magnetic field, the number of truly habitable worlds might drop significantly. This is sometimes called the rare Earth hypothesis, the idea that Earth-like planets with all the necessary conditions for complex life are extremely rare in the galaxy. Not impossible, but uncommon enough that we might never find another one within reach. On the other hand, we might be overestimating the importance of magnetic fields. Life on Earth has survived multiple magnetic reversals, periods when the field was weak and chaotic. Maybe life is more resilient than we think. Maybe atmospheres can survive longer without magnetic protection than our models suggest. Or maybe there are alternative forms of protection we haven't considered. A planet with a very thick atmosphere might not need a magnetic field. The atmosphere itself could provide enough shielding. Or a planet orbiting a calm, stable star might not be subjected to intense stellar winds, so even a weak magnetic field or no field at all could be sufficient. We're reasoning from a sample size of 1, Earth, and that's always dangerous in science. The universe might be full of habitable worlds that don't fit our assumptions. What's certain is that every discovery teaches us something new. Every exoplanet we find, every measurement we make refines our understanding of what makes a planet habitable. And at the center of that understanding is Earth's magnetic field, our template, our reference point. We study Earth to understand other worlds. We measure our magnetic field to predict what we might find elsewhere. And in doing so, we gain a deeper appreciation for the delicate balance that makes our own world livable. Think about this for a moment. The magnetic field is a gift of physics. It's not designed. It's not intentional. It's simply what happens when a planet of the right size and composition cools slowly enough to maintain a molten outer core for billions of years. And yet, without that accidental, unintended consequence of planetary formation, life might never have evolved here. Intelligence might never have emerged. You might never have existed. It's a reminder that we're here because of a long chain of lucky accidents, each one necessary, each one unlikely, but all of them conspiring to create the conditions for consciousness to arise and contemplate its own existence. There's a word for this in philosophy: the anthropic principle, the observation that the universe appears fine-tuned for life, because if it weren't, we wouldn't be here to observe it. It's a tautology, in a way, but it's also profound. We exist in a universe where the constants of physics, the properties of matter, the behavior of stars and planets all happen to allow for life. If any of those things were different, we wouldn't be here. And so we find ourselves in a universe that seems designed for us, even though it's not designed at all. We're the outcome of trillions of random events, filtered by the requirement that we must exist to ask the question. The magnetic field fits into this story. It's one of the many factors that had to be just right. Not too strong, not too weak, not too stable, not too chaotic. Generated by a core that's neither fully solid nor fully molten, but somewhere in between, with just the right amount of heat and rotation. It's extraordinary when you think about it. And it's humbling, because it reminds us that we're not the inevitable product of cosmic evolution. We're a possibility that happened to be realized on one planet, around one star, in one galaxy, among trillions. We might be alone, or we might be one of countless civilizations scattered across the cosmos, each one marveling at the magnetic field that protects their world, each one wondering if they're unique. As you lie there, drifting closer to sleep, let that thought settle into your mind. You're part of something vast and improbable. You exist because of an invisible shield generated by molten metal thousands of miles beneath you. A shield that's been operating for billions of years, protecting this planet, allowing life to flourish, giving evolution the time it needed to produce conscious beings capable of understanding the very forces that made them possible. That's not a miracle, it's physics. But it feels miraculous nonetheless. In the next part of our journey, we'll explore one final mystery: the connection between Earth's magnetic field and human history. Have magnetic reversals or fluctuations influenced civilizations? Could ancient peoples have sensed changes in the field? And what does the future hold as we venture out into the solar system, leaving the protection of Earth's magnetosphere behind. What does it mean to be human in a universe where magnetic fields, invisible and indifferent, determine which worlds can cradle life and which remain barren? Let's travel backward through time for a moment. Not all the way back to Earth's formation, but just a few thousand years, to the time when humans first began recording their observations of the world. Ancient peoples didn't understand the magnetic field in scientific terms, but they experienced its effects. The compass, as I mentioned, was known to the Chinese by the 11th century, perhaps earlier. But there's evidence that humans might have been aware of magnetic phenomena long before that. In ancient Greece, around 600 BCE, a philosopher named Thales of Miletus wrote about lodestones, naturally magnetic rocks that could attract iron. He was fascinated by this invisible force. Some ancient texts describe lodestones as having souls or spirits because they could move things without touching them. This was profound for people who had no concept of fields or forces acting at a distance. Everything they understood about the world involved direct contact. You push something, it moves. You pull something, it comes toward you. But a lodestone could pull iron toward itself across empty space. It seemed almost magical. The word magnet itself comes from Magnesia, a region in ancient Greece where lodestones were found. These stones, pieces of magnetite that had been naturally magnetized by lightning strikes or by Earth's magnetic field over long periods, were curiosities, objects of wonder and speculation. No one knew what caused the attraction. They could observe it, experiment with it, even use it for practical purposes, but they couldn't explain it. It would take nearly 2,000 years before scientists like William Gilbert began to understand that Earth itself was magnetic, and that lodestones were simply responding to that field. But here's an intriguing question. Could ancient peoples have noticed changes in the magnetic field? Could they have sensed when the field was weakening or when the poles were drifting? The answer is complicated. The changes happen slowly, over decades and centuries. A person living through one of these changes wouldn't notice it in their lifetime. The compass would still point roughly north. Lodestones would still attract iron. But over generations, over centuries, someone keeping careful records might notice that the compass was pointing in a slightly different direction than it used to. That magnetic north had shifted. There's some evidence that ancient navigators were aware of magnetic declination, the difference between magnetic north and true north. Chinese and Arab sailors in the medieval period knew that the compass didn't point exactly toward the geographic pole. They had tables of corrections, adjustments they made based on their location and the season. Whether they understood that these corrections were changing over time is unclear. The records are fragmentary, often ambiguous, but it's possible that some civilizations, particularly those with long traditions of careful observation and record-keeping, noticed the slow drift of the magnetic poles. Could magnetic changes have influenced human history in more dramatic ways? Some researchers have speculated about connections between geomagnetic activity and historical events. For instance, during periods of intense solar activity, when geomagnetic storms were frequent, the auroras would have been visible at lower latitudes than usual. People in southern Europe, the Middle East, even North Africa might have seen strange lights in the sky, curtains of red and green shimmering above the horizon. Without scientific understanding, these would have been interpreted as omens, signs from the gods, portents of war or plague or other disasters. There are historical accounts of strange sky phenomena that might have been auroras. Ancient Roman historians described blood-red skies on certain nights. Chinese astronomers recorded unusual lights and colors in the heavens. Medieval European chronicles mentioned fires in the sky, flames that didn't burn, lights that moved and danced without sound. Some of these might have been auroras caused by major solar storms. And if those storms coincided with other significant events, wars, famines, the deaths of kings, people would have connected them, seen causation where there was only correlation. The sky turned red, and then the emperor died. Therefore, the red sky was a warning, a message from the heavens. This is how humans make sense of the world. We look for patterns, connections, meaning. And in a time before science, when the mechanisms of nature were mysterious, it was natural to interpret unusual phenomena as supernatural. The magnetic field and its effects, the auroras, the behavior of compasses, the attraction of lodestones. All of these must have seemed like manifestations of hidden forces, invisible spirits, divine influence. And, in a way, they were right. There were hidden forces at work. They just weren't supernatural. They were natural, governed by physics, but so far beyond everyday experience that they might as well have been magic. Now, let's think about what it means to leave Earth's magnetic field behind. As humanity ventures into space, we're leaving the protection of the magnetosphere for the first time in our evolutionary history. Every human who has ever lived, until the mid-20th century, lived their entire life within the magnetosphere. Even high-altitude mountain climbers, even people living on the Tibetan Plateau, were still inside the protective bubble. But astronauts are different. When they launch into orbit, when they travel to the moon, when they eventually journey to Mars, they're leaving that protection. They're exposed to the full force of space radiation in a way no human has ever been before, at least not for extended periods. The Apollo astronauts who traveled to the moon in the 1960s and 70s spent only a few days outside the magnetosphere. They were lucky. No major solar storms occurred during their missions. If one had, the radiation dose could have been severe, possibly fatal. The astronauts wore no specialized radiation shielding. The spacecraft hull provided some protection, but not much. They were vulnerable, and they knew it. There are stories of Apollo astronauts seeing flashes of light even with their eyes closed, caused by cosmic rays passing through their eyeballs and striking the retina. These flashes, called phosphenes, were a direct experience of space radiation, particles from distant supernovae traveling through the astronauts' heads. It was a reminder that space is not empty. It's filled with invisible particles, traveling at relativistic speeds, constantly bombarding anything that ventures beyond Earth's protective shield. Future missions to Mars will face this challenge on a much larger scale. The journey to Mars takes 6 to 9 months each way, depending on the alignment of the planets. During that time, astronauts would be outside the magnetosphere, exposed to the solar wind, cosmic rays, and any solar storms that happen to occur. A mission to Mars and back could last 2 to 3 years, including time spent on the Martian surface. That's a long time to be exposed to elevated radiation levels. Even with shielding, the cumulative dose would be significant. This raises ethical questions. How much risk are we willing to accept? Astronauts are brave, willing to take risks that most people wouldn't consider. But there's a difference between known risks and uncertain ones. We know that radiation increases cancer risk, yay. But we don't know exactly how much risk a Mars mission would entail, because we've never sent humans on such a journey. The models and simulations give us estimates, but there's always uncertainty. And then there's the question of equity. Who gets to go? Who decides? Space exploration has historically been dominated by a small number of wealthy nations. If we're going to send humans to Mars, to establish permanent settlements beyond Earth, who will those humans be? Will it be a diverse, representative sample of humanity, or will it be a select few, chosen by governments or corporations? There's also the question of what we might become if we live beyond Earth's magnetosphere for generations. Radiation causes mutations. Most mutations are harmful or neutral, but occasionally, a mutation provides some advantage. If humans lived on Mars for thousands of years, exposed to higher radiation levels than on Earth, would we evolve differently? Would Martian humans, descendants of Earth settlers, develop biological adaptations to cope with radiation? Perhaps more efficient DNA repair mechanisms or cellular processes that tolerate higher levels of genetic damage? It's speculative, but it's not impossible. Evolution doesn't care where you are. It only cares about survival and reproduction. If certain genetic variations help individuals survive and pass on their genes in a high-radiation environment, those variations will become more common over time. But that's thinking very far ahead. First, we need to get there, And getting there safely means protecting astronauts from radiation. One approach, as I mentioned, is physical shielding. Surround the spacecraft or habitat with materials that absorb radiation. Water is effective, hydrogen-rich, and relatively abundant in space if you know where to find it. Asteroids and comets contain water ice. The Moon has water ice in permanently shadowed craters near the poles. Mars has water ice underground and in its polar caps. Future space missions might harvest this water, not just for drinking and growing food, but for radiation shielding. Imagine a spacecraft with a shell of water ice several feet thick surrounding the crew compartment. The ice absorbs incoming radiation, and as an added bonus, it slowly melts and provides drinking water over the course of the mission. Another approach is active shielding. Instead of relying on mass to absorb radiation, you create a magnetic field. Around the spacecraft, an artificial magnetosphere that deflects charged particles the way Earth's magnetosphere does. This is technologically challenging. You'd need powerful magnets or superconducting coils, and you'd need a significant power source to keep them running. But it's not science fiction. Engineers have designed concepts for magnetic shields that could protect spacecraft. The field doesn't need to be as strong as Earth's because it only needs to protect a small volume, the spacecraft, not an entire planet. And it only needs to deflect the most dangerous particles, the high-energy protons and heavy ions that cause the most biological damage. Some designs use plasma-based shielding, creating a cloud of charged particles around the spacecraft that interacts with incoming radiation and reduces the dose reaching the crew. Others use electric fields to repel particles. There are many ideas, some more practical than others, but all of them are being researched. Because if humanity is serious about becoming a spacefaring species, about establishing permanent settlements on the Moon, Mars, and eventually beyond, we need to solve the radiation problem. We can't rely on luck, hoping that no major solar storms occur during critical missions. We need reliable, robust protection. And this brings us back to Earth's magnetic field. It's easy to take it for granted when you've lived under its protection your whole life. But the moment you leave it, you realize how essential it is. Astronauts who have traveled beyond low Earth orbit, the Apollo astronauts, and eventually the crew of future lunar or Martian missions, have a unique perspective. They've experienced what it's like to be unprotected, exposed, vulnerable. They've seen Earth from the outside, a small blue marble hanging in the darkness, surrounded by an invisible shield that makes life possible. That perspective changes you. It makes you appreciate the fragility of our existence, the delicate balance of conditions that allow us to live and thrive. There's a famous photograph taken during the Apollo 8 mission in 1968. It's called Earthrise, and it shows Earth rising above the lunar horizon, a brilliant blue and white sphere against the black void of space. That image had a profound impact on people. It showed Earth as a whole, a single interconnected system, with no borders, no divisions, just a planet floating in space. And that planet, as we now know, is wrapped in a magnetic field that's been protecting it for billions of years. You can't see the field in the photograph, but it's there, doing its job, deflecting the solar wind, preserving the atmosphere, making the blue and white colors possible. The astronauts who took that photograph, Frank Borman, Jim Lovell, and Bill Anders, were the first humans to leave Earth's magnetosphere. They orbited the Moon, looking back at their home planet from 250,000 miles away. And what they saw changed them. They returned to Earth with a new understanding of how small and precious our world is, how isolated we are in the vastness of space, and how important it is to protect and preserve the only home we've ever known. That message, that perspective, is part of the legacy of space exploration. It's not just about going to other worlds. It's about understanding our own world more deeply, appreciating what we have, and recognizing that the conditions that make Earth habitable are rare and perhaps fragile. But let's bring this back to something more immediate, more personal. You, lying there, listening to these words. You've never left Earth's magnetosphere. You've spent your entire life under its protection, and yet you're connected to space in ways you might not realize. The atoms in your body were forged in stars. The oxygen you breathe was produced by ancient cyanobacteria billions of years ago. The water you drink has been cycled through the atmosphere and oceans for eons. You're not separate from the cosmos. You're part of it. And the magnetic field that protects you is part of a planetary system that's been operating since long before humans existed and will continue operating long after we're gone. There's something comforting about that, isn't there? The magnetic field doesn't care about politics, economics, wars, or civilizations. It just exists, doing what it does, generated by the slow cooling of the planet, indifferent to the life it protects. It's a reminder that we're passengers on this planet, not its masters. We didn't create the conditions for our existence. We inherited them. And our responsibility, if we have one, is to understand those conditions, to preserve them if we can, and to appreciate the improbable chain of events that led to us being here at all. As humans venture into space, as we establish footholds on the Moon and Mars, as we perhaps one day travel to the moons of Jupiter or Saturn, we'll carry with us the knowledge gained from studying Earth's magnetic field. We'll use that knowledge to protect ourselves, to create artificial magnetospheres, to shield our habitats and spacecraft. But we'll also carry with us a sense of loss, a nostalgia for the natural protection we left behind. Earth's magnetic field is unique in our experience. It's the only planetary magnetic field that has directly protected human life. Every other magnetic field we encounter, whether on Jupiter's moons or around distant exoplanets, will be foreign, different, something to study, but not something that shaped us. And maybe, thousands of years from now, if humans have spread across the solar system and beyond, there will be people who have never experienced Earth's magnetosphere. They'll be born on Mars, or in orbital habitats, or on moons of gas giants, living under artificial magnetic shields or in heavily shielded underground cities. To them, Earth's magnetic field will be a historical curiosity, something their ancestors relied on, but that they've never known. They'll learn about it in schools, study it in history classes, but it won't be part of their lived experience. And perhaps they'll feel a sense of longing, a desire to return to the origin, to experience the natural protection that shaped their species for millions of years. Or maybe they won't. Maybe they'll adapt so completely to life beyond Earth that the magnetosphere will seem quaint, a relic of a time when humans were confined to a single planet. Evolution doesn't look backward. It only moves forward, adapting to whatever environment exists. If the future of humanity is in space, then future humans will be space-adapted, comfortable with radiation shielding and artificial gravity and recycled air. They'll be different from us in ways we can't fully imagine, but they'll still carry the legacy of Earth, the genetic heritage shaped by billions of years of evolution under the protection of a magnetic field. Can you imagine that future? Can you picture humans living on Mars, looking up at a sky without a blue atmosphere, protected by domes and underground habitats, shielded by technology rather than by a planetary magnetic field? It's a strange thought. We've spent our entire evolutionary history on Earth, shaped by its gravity, its atmosphere, its magnetic field. Leaving all of that behind means becoming something new, something adapted to a different set of conditions. We'll still be human in some sense, but we'll be changed. And maybe that's okay. Change is what life does. It adapts, it evolves, it finds ways to survive in new environments. But for now, for you, lying there in the quiet of the night, Earth's magnetic field is still there, invisible and constant, wrapping around the planet, deflecting the solar wind, protecting the atmosphere, making the air you breathe possible. It's been there your whole life. It was there for your parents, your grandparents, your ancestors stretching back millions of years. And it will be there for your children, and their children, and countless generations to come, until someday, far in the future, Earth's core cools and the field fades away. But that day is so distant that it's almost meaningless to contemplate. For all practical purposes, the magnetic field is eternal, a fundamental part of what makes Earth Earth. So rest easy. The shield is holding. The invisible guardian is at its post, and as you drift into sleep, you can let go of worry, let go of the need to understand everything, and simply exist, protected and safe, on a small planet in a vast universe, wrapped in a magnetic field that asks nothing of you but gives you everything. In our next part, we'll bring this journey toward its conclusion, exploring the deepest questions. What does the magnetic field tell us about the nature of existence, about our place in the cosmos, and what would it mean to lose it, not gradually over billions of years, but suddenly, catastrophically? What would Earth become without its invisible shield? And how would that change everything we know? Let's ask a question that might seem impossible to answer. What would Earth look like without its magnetic field? Not in the distant future when the core naturally cools, but right now. Imagine if, tomorrow, the geodynamo simply stopped. The molten iron in the outer core froze solid, or the convection patterns that generate the field suddenly ceased. What would happen? At first, nothing. The change would be invisible. You'd wake up, go about your day, and notice nothing different. The sky would still be blue. The sun would still rise and set. Birds would still sing. Life would continue exactly as it always has. Because the magnetic field is invisible, its sudden absence wouldn't create any immediate, obvious change. Your compass would stop working. Or rather, it would point randomly, responding to local magnetic anomalies in rocks and buildings rather than to a global field. But how often do you actually use a compass? For most people, the answer is never. GPS satellites would continue to work, at least at first. The sun would still shine. The atmosphere would still be there. But slowly, over days and weeks and months, things would start to change. The first sign would be the auroras. Without a magnetic field to funnel solar particles toward the poles, the auroras would appear everywhere, or nowhere. The organized pattern, the beautiful curtains of light confined to high latitudes, would vanish. Instead, solar particles would hit the atmosphere randomly across the entire globe. You might see faint, diffuse glows in the sky, but they wouldn't be the spectacular displays we associate with the northern and southern lights. They'd be scattered, chaotic, unpredictable. Satellites would start failing. Without the magnetosphere to deflect the solar wind, satellites in orbit would be exposed to much higher levels of radiation. Electronics would degrade faster. Solar panels would be damaged by high-energy particles. Communication satellites, GPS satellites, weather satellites, all of them would have shorter lifetimes. Some would fail within weeks or months. Others might last a few years, but eventually, the accumulated radiation damage would overwhelm them. And as satellites failed, the services they provide would disappear. GPS navigation would become unreliable. Satellite television and radio would go dark. Weather forecasting, which relies heavily on satellite data, would become less accurate. The International Space Station, if it still existed at the time the field vanished, would become a death trap. Astronauts on board would be exposed to radiation levels far beyond safe limits. They'd need to evacuate immediately, return to Earth while they still could. Any future space missions would require dramatically more shielding, making them heavier, more expensive, and more difficult to launch. Humanity's ability to operate in space would be severely curtailed, at least until we developed better radiation protection technology. On the ground, most people would still be safe, at least initially. Earth's atmosphere is thick enough to absorb most incoming radiation. The ozone layer, in particular, blocks harmful ultraviolet light. But here's the problem. The solar wind doesn't just deliver radiation, it also strips away atmosphere. This happens slowly, particle by particle, but over time, the effect is cumulative. Mars lost most of its atmosphere this way after its magnetic field shut down. Earth has a thicker atmosphere to start with, and Earth's gravity is stronger, which helps hold the atmosphere in place. But without the magnetic field, atmospheric erosion would begin. How long would it take? That's the question scientists have tried to answer using computer models. The estimates vary, but most suggest it would take hundreds of millions of years for Earth to lose a significant fraction of its atmosphere through solar wind erosion. That sounds like a long time, and it is. You wouldn't live to see the effects. Neither would your children or their children for 1,000 generations. But on geological timescales, it's relatively quick, and the process would be irreversible. Once the atmosphere is gone, it's gone. There's no way to get it back without somehow restarting the geodynamo or importing vast quantities of gas from elsewhere in the solar system. The ozone layer would be particularly vulnerable. Ozone, O3, 3 oxygen atoms bonded together, is created when ultraviolet light from the sun breaks apart ordinary oxygen molecules, O2, and the free oxygen atoms recombine with other O2 molecules. It's a delicate balance. Without the magnetic field deflecting high-energy particles, more of those particles would reach the upper atmosphere, breaking apart oxygen and nitrogen molecules. This could disrupt the formation of ozone, thinning the ozone layer. A thinner ozone layer means more ultraviolet radiation reaching the surface. And ultraviolet radiation is harmful to life, damaging DNA, causing mutations, increasing cancer rates. Plants and animals that rely on UV-sensitive processes would struggle. Phytoplankton in the oceans, which form the base of the marine food chain, are particularly vulnerable to UV radiation. If phytoplankton populations declined, the entire oceanic ecosystem could collapse. Fish populations would crash. Marine mammals would starve. And because the ocean plays a crucial role in regulating Earth's climate, absorbing carbon dioxide and releasing oxygen, a collapse of marine ecosystems could trigger cascading climate changes. Temperatures could rise as carbon dioxide accumulated in the atmosphere. Ice caps could melt. Sea levels could rise. The climate system, already delicately balanced, could tip into a new state, one far less hospitable to life. And through all of this, the solar wind would continue its work, slowly, patiently, stripping away the atmosphere. The thicker the atmosphere to start with, the longer it takes. But the process is relentless. Given enough time, Earth could end up like Mars. Cold, dry, barren. The oceans would evaporate. The water molecules split apart by solar radiation. Hydrogen, the lightest element, would escape into space. Oxygen would react with rocks, oxidizing the surface, turning it red like Mars. The blue planet would become a red planet, a dead world, a cautionary tale of what happens when a magnetic field fails. But let's be clear, this is not going to happen. Earth's magnetic field is not about to shut down. Even if it reverses, which it might do in the next few thousand years, the field doesn't disappear during a reversal. It weakens, yes. It becomes chaotic, yes. But some level of protection remains. Life has survived hundreds of magnetic reversals over the past billion years. There's no reason to think the next one will be any different. The scenario I just described, the sudden, permanent loss of the magnetic field, is purely hypothetical. It's a thought experiment, a way of understanding what the magnetic field does by imagining what would happen without it. And what it shows is this: the magnetic field is not optional. It's not a nice-to-have feature of Earth. It's essential. Without it, Earth would eventually become uninhabitable, at least on the surface. Life might persist in the deep oceans or underground, in places shielded from radiation by water and rock. But the rich, diverse biosphere we know, the forests and grasslands, the coral reefs and rainforests, the birds and mammals and insects, all of it depends on the protection provided by the magnetic field. Take away that protection, and you take away the conditions that make complex life possible. This leads to a deeper question, one that touches on philosophy and the meaning of existence. Why does Earth have a magnetic field? Not in the mechanistic sense we know it's generated by the geodynamo, but in the larger sense. Why did the conditions align such that Earth has the right size, the right composition, right amount of internal heat to sustain a magnetic field for billions of years? Is it chance? Is it inevitable? Is it common in the universe or rare? We don't know the answer yet. We're still in the early stages of exploring exoplanets, still learning what kinds of worlds exist out there. But from what we've seen so far, Earth-like planets might not be as common as we once hoped. Most of the exoplanets discovered are either gas giants, massive worlds like Jupiter, or super-Earths, rocky planets significantly larger than Earth. True Earth analogs, planets about the same size as Earth, orbiting sun-like stars at the right distance for liquid water, are rarer. And of those, how many have magnetic fields? How many have the right internal structure to generate and sustain a protective magnetosphere? We simply don't know. There's a concept in astrobiology called the Goldilocks principle. For a planet to be habitable, everything has to be just right. Not too hot, not too cold, not too big, not too small. The right kind of star, the right orbital distance, the right atmospheric composition, and yes, the right magnetic field. Too many things have to align perfectly. Change any one of them, and the planet becomes uninhabitable. This suggests that habitable worlds might be extraordinarily rare, perhaps so rare that Earth is the only one in our galaxy, or even in the observable universe. On the other hand, the universe is unimaginably vast. There are hundreds of billions of galaxies, each containing hundreds of billions of stars. Even if habitable planets are rare, 1 in a million or 1 in a billion, the sheer number of opportunities means there should be many such worlds out there. The question is whether we'll ever find them, whether we'll ever be able to reach them or communicate with civilizations that might exist on them. And that's where the magnetic field enters the story again. Because if we want to search for life on other worlds, one of the things we should look for is magnetic fields. A planet with a magnetic field is a planet that's geologically active, that has a molten interior, that's dissipating heat. That's a good sign. It means the planet is alive in a geological sense. It's not a cold, dead rock. It has the energy and the dynamics to potentially support life. So when astronomers develop the next generation of telescopes and instruments capable of detecting magnetic fields around exoplanets, they'll be looking not just out of scientific curiosity, but because magnetic fields are a biosignature, an indirect sign that a planet might be habitable. But even if we find other worlds with magnetic fields, even if we discover life elsewhere in the universe, it won't diminish Earth's significance. Because Earth is where we evolved. Earth is where consciousness first emerged, at least as far as we know. Earth is the planet that nurtured our ancestors for millions of years, providing the stable, protected environment they needed to survive, to evolve, to eventually develop intelligence and technology and the ability to ask questions about the universe. The magnetic field was part of that story, an invisible guardian that never wavered, never failed, always there in the background, doing its job. There's a kind of poetry to it, don't you think? The most important protective system on the planet is invisible. You can't see it, can't touch it, can't sense it directly, and yet, it's been keeping you alive since the moment you were born. Before you were born even. Before your parents were born. Before humans existed. It's been there for billions of years, a silent witness to the entire history of life on Earth. It saw the first single-celled organisms appear in the oceans. It was there when those cells learned to photosynthesize, producing oxygen and transforming the atmosphere. It watched as life colonized the land, as forests spread across the continents, as dinosaurs rose and fell, as mammals diversified, as primates evolved, as humans emerged. And through all of that, the magnetic field was constant. It weakened and strengthened. It reversed polarity. It drifted and fluctuated. But it never stopped. It never gave up. It kept deflecting the solar wind, kept protecting the atmosphere, kept making life possible. And it's still doing that right now, as you lie there, breathing air that wouldn't exist without it, protected from radiation you'll never see, safe in a way you'll never fully appreciate because the danger is invisible. If you could somehow perceive the magnetic field, what would it look like? Maybe it would shimmer, like heat waves rising from hot pavement. Maybe it would glow faintly, a soft blue or green aura surrounding the planet. Maybe it would pulse, responding to changes in the solar wind, brightening when the sun is active, dimming during quiet periods. You could watch solar storms approach, see them collide with the magnetosphere, see the field lines bend and stretch and snap back. You could see the particles funneling toward the poles, streaming down into the atmosphere, creating auroras. It would be beautiful, a cosmic light show happening all the time, invisible to your eyes, but always there. But you can't see it. So instead, you have to imagine it. You have to take the knowledge you've gained, the understanding of how the magnetic field works, what it does, why it matters, and build a mental picture. Close your eyes. Not to sleep yet, but to visualize. Picture Earth from space, a blue marble against the black void. Now picture the magnetic field extending out from the planet, invisible but real. Curving lines of force reaching tens of thousands of miles into space. Picture the solar wind approaching, a stream of charged particles flowing from the sun at 1,000,000 miles per hour. Watch as those particles encounter the magnetosphere. Watch them bend around it, deflected, diverted, channeled toward the poles. See the magnetotail stretching out behind the planet, a long wake in the solar wind, like the wake behind a boat moving through water. And now, bring your awareness back down to Earth. Back down through the magnetosphere, through the Van Allen radiation belts, through the upper atmosphere, through the clouds, down to the surface, to the room where you're lying, to your body, warm and breathing, alive. You're inside the protective bubble. You've always been inside it. And barring some catastrophic event, you'll spend your entire life inside it. The magnetic field is your birthright, a gift from the planet. A consequence of physics and chemistry operating on a scale so vast that it took billions of years to create the conditions you now benefit from. Does that make you feel small? Or does it make you feel connected, part of something larger than yourself? Both, perhaps. You're insignificant in the cosmic scale, a tiny organism on a tiny planet in a vast universe. But you're also extraordinary, a conscious being capable of understanding the forces that shaped you, capable of contemplating your own existence and the improbable chain of events that led to you being here. The magnetic field doesn't care about you. It doesn't know you exist. It's not protecting you specifically. It's just doing what it does, following the laws of physics, responding to the motion of molten iron thousands of miles below. And yet, in protecting the planet, it protects you. In making life possible, it made you possible. That's the paradox of existence. The universe is indifferent to us, and yet we're here because of it. The forces that govern stars and planets and magnetic fields are blind, uncaring, operating according to mathematical laws that have no concept of meaning or purpose. And yet, those forces created the conditions for consciousness to emerge, for beings like us to arise and ask why. We're the universe becoming aware of itself. Matter contemplating matter, a temporary spark of consciousness in an otherwise unconscious cosmos. The magnetic field is a reminder of that. It's a physical phenomenon, explainable through science. Nothing mystical or supernatural about it. And yet, it's also miraculous, in the sense that it's one of many factors that had to align perfectly for life to exist. If Earth were smaller, the core would have cooled faster. The geodynamo would have shut down, and there'd be no magnetic field. If Earth were larger, the gravity might be so strong that the atmosphere would be too thick, the pressure at the surface too high for life as we know it. If Earth's rotation were slower, the geodynamo might not generate a strong enough field. If the iron content of the core were different, the field might not form at all. Every detail matters. Every condition has to be just right. And somehow, on this one planet, orbiting this one star, in this one galaxy, all the conditions aligned. The size was right. The composition was right. The rotation was right. The distance from the sun was right. And the result is a world wrapped in an invisible shield, protected from the hazards of space, stable enough for life to emerge and evolve over billions of years. That's not a miracle in the religious sense. but it's miraculous in the sense of being improbable, unlikely, extraordinary. We exist because of a series of cosmic accidents, each one necessary, each one contingent on countless factors that could easily have been different. So, as we approach the end of this journey through the invisible, as you drift closer to sleep, hold on to that thought. You're here because of the magnetic field and 1,000 other factors, all working together, creating the conditions for your existence. You didn't earn this. You didn't deserve it. You simply inherited it, a gift from the universe, a set of circumstances that made consciousness possible. What you do with that gift, how you live your life, what meaning you create, that's up to you. But the foundation, the invisible support, that makes everything else possible, has been there all along, asking nothing, giving everything. In the final part of our journey, we'll bring everything together. We'll step back and see the whole picture, the magnetic field in the context of Earth's history and humanity's future. We'll explore what it means to be alive in a universe governed by invisible forces, protected by shields we'll never see, connected to processes operating on scales we can barely comprehend. And we'll ask one last question. If you could send a message to future generations, to humans living 1,000 years from now, maybe on Earth, maybe on Mars, maybe scattered across the solar system, what would you tell them about the magnetic field, about the invisible guardian that protected their ancestors and made their existence possible? What wisdom would you pass on? We've traveled far together on this journey. From the surface of Earth down into the molten core, out into space to see the magnetosphere stretching toward the stars, back through time to witness magnetic reversals, and forward into a future where humans might venture beyond the protection that has sheltered us for our entire evolutionary history. Now, as we come to the end, let's gather all these pieces together and see what they reveal. The magnetic field is invisible, but it's everywhere. It extends from the deepest part of Earth's core to the farthest reaches of the magnetosphere, encompassing the entire planet and beyond. You live inside this field. You've never been outside it. Every breath you take, every step you walk, every thought you think, happens within the protective embrace of Earth's magnetic shield. And you share this protection with every living thing on the planet. The trees growing in forests, their roots deep in the soil, are inside the magnetic field. The birds, migrating across continents, navigating by that same field, are inside it. The whales singing in the depths of the ocean, the bacteria in the soil, the insects in the grass, all of them, all of us, live inside this invisible bubble. The field doesn't distinguish between species. It doesn't favor humans over other forms of life. It protects everything equally, indifferently, simply by existing. That's a humbling thought. We like to think we're special, that the universe cares about us somehow. But the magnetic field is a reminder that we're not special in any cosmic sense. We're just one more form of life that happened to evolve on a planet that happened to have the right conditions. The field would exist whether we were here or not. It existed for billions of years before humans appeared, and it will continue to exist long after we're gone. And yet, there's something special about being able to understand it. Out of all the species that have ever lived on Earth, humans are the only ones who can comprehend the magnetic field, who can measure it, study it, explain how it works. We're the only ones who can look at a compass and understand that it's responding to a force generated thousands of miles below the surface. We're the only ones who can observe auroras and know that they're caused by solar particles colliding with atmospheric gases along magnetic field lines. We're the only ones who can predict when the field might reverse and prepare for the consequences. This ability to understand is what makes us human. Not our strength. We're weak compared to many animals. Not our speed. We're slow. Not our senses. Many creatures can see, hear, and smell far better than we can. What makes us unique is our capacity for abstraction, for pattern recognition, for building mental models of invisible phenomena. We can understand things we can't directly perceive. We can imagine the unimaginable. We can contemplate our place in a universe that's billions of years old and trillions of miles across. That's extraordinary. And that understanding comes with responsibility. Because once you know how the magnetic field works, once you understand how essential it is, you can't unknow it. You can't go back to the innocent ignorance of our ancestors who looked at the sky and saw gods and spirits rather than physics and chemistry. You know now that Earth's habitability depends on a delicate balance of factors, any one of which could change. The magnetic field could weaken or reverse. The sun could become more active, producing more frequent and more powerful solar storms. Human activity could alter the atmosphere in ways that affect the ozone layer or the climate system. The future is uncertain, not predetermined. But that uncertainty isn't necessarily frightening. It's also an opportunity. Because if the future is uncertain, it means we have agency, the ability to influence what happens. We can study the magnetic field more carefully, build better models, improve our predictions. We can prepare for space weather events, protecting our satellites and power grids. We can reduce our impact on the environment, preserving the atmospheric conditions that work in concert with the magnetic field to protect life. We can even imagine, in the distant future, creating artificial magnetic fields for other worlds, giving Mars or the moons of Jupiter the protection they lack. The magnetic field has protected us without asking for anything in return. It's been a gift, freely given by the physics of planetary formation and the slow cooling of Earth's interior. But now that we understand it, we have the opportunity to become not just passive recipients of that protection, but active participants in preserving it, in extending it, in ensuring that future generations can continue to benefit from it. Think about those future generations for a moment. Your children, if you have them, their children, and their children's children, extending forward through time. They'll live in a world you can barely imagine, with technologies you can't predict, facing challenges you can't foresee. But they'll still be protected by the magnetic field, unless something catastrophic happens. They'll still breathe air held in place by Earth's gravity and protected from erosion by the magnetosphere. They'll still see auroras dancing in the polar skies when solar storms arrive. They'll still live on a planet wrapped in an invisible shield. Will they know about it? Will they appreciate it? That depends on us. If we pass on the knowledge, if we tell the story of the magnetic field, if we ensure that education includes not just what the field is, but why it matters, then yes, they'll know. They'll understand their place in the cosmic order. They'll appreciate the invisible forces that make their lives possible. But if we forget, if we take the field for granted and never teach the next generation about it, then that knowledge could be lost. And with it, the appreciation for how precious and fragile our habitability really is. So in a sense, this journey we've taken together is not just about understanding a scientific phenomenon. It's about passing on a legacy. The legacy of knowledge, of wonder, of appreciation for the invisible forces that shape our existence. Every person who learns about the magnetic field, who understands its role in making life possible, becomes a carrier of that legacy. You can share it with others. You can talk about it with friends, with family, with children. You can help ensure that the knowledge persists, that future generations don't forget the invisible guardian that's been protecting Earth for billions of years. But there's another aspect to this, something more philosophical. The magnetic field is a reminder that reality is richer than what we can directly perceive. You go through life experiencing the world through your senses. You see colors, hear sounds, feel textures, taste flavors, smell scents, but your senses only show you a narrow slice of reality. You can't see ultraviolet or infrared light, though both exist. You can't hear ultrasonic or infrasonic sounds, though many animals can. You can't sense magnetic fields directly, though they're all around you. The universe is full of phenomena that exist beyond the range of human perception. Science is the tool we've developed to extend our senses, to see the invisible, to measure the unmeasurable. Instruments like magnetometers, telescopes, microscopes, they're extensions of ourselves, ways of perceiving what our biology alone cannot detect. And through those instruments, through careful observation and mathematical reasoning, we've built a picture of reality that's far more complex and beautiful than what our senses alone reveal. The magnetic field is just one example. It's invisible, but it's real, and it's essential. And there are countless other invisible phenomena. Dark matter holding galaxies together. Quantum fields, underlying all of physical reality. Space-time itself curving in the presence of mass and energy. We live in a universe we're only beginning to understand, a universe full of mysteries, some of which we've solved, many of which remain. The magnetic field was once a mystery. People knew about lodestones, knew that compasses worked, but they didn't know why. Now we know. We've solved that mystery. We've explained how the field is generated, why it exists, what it does. And in solving that mystery, we've opened new ones. What exactly triggers magnetic reversals? How will the field evolve over the next 1,000 years? Are magnetic fields common on other Earth-like planets, or rare? We don't have all the answers yet, but we're working on it, building knowledge piece by piece, generation by generation. And that's the beauty of science. It's cumulative. Each generation builds on what the previous generation discovered. Isaac Newton said he stood on the shoulders of giants, meaning he built on the work of those who came before him. And every scientist since has done the same. The knowledge we have today about the magnetic field was built by thousands of researchers over hundreds of years, each one contributing a small piece to the puzzle. And future researchers will build on that foundation, adding new pieces, refining the picture, correcting errors, extending the understanding further. You're part of that tradition, even if you're not a scientist. Because by learning about the magnetic field, by taking the time to understand it, you're carrying forward the torch of knowledge. You're keeping the flame of curiosity alive. And that matters. Because a civilization that stops asking questions, that stops trying to understand the universe, is a civilization in decline. Curiosity is what drives progress, what pushes us to explore, to discover, to grow. And the magnetic field, with its invisible presence and essential role, is the perfect subject for curiosity. It rewards those who study it with insights into how planets work, how life persists, how the cosmos operates. Now, as we near the end of this journey, I want you to do something. I want you to take a moment, right now, to acknowledge the magnetic field. You can't see it, but you know it's there. Feel the air moving in and out of your lungs, air that exists because the magnetic field helped preserve the atmosphere. Feel the warmth of your body, warmth powered by food that grew under the protection of that same field. Listen to the silence around you, a silence that exists because you're on a planet stable and protected enough for quiet moments to occur. The magnetic field is working right now. Above your head, tens of thousands of miles up, the magnetopause is holding the line against the solar wind. The Van Allen belts are trapping dangerous particles, keeping them away from the surface. The field lines are funneling some particles toward the poles, where they might be creating auroras that you'll never see, but that are happening nonetheless. And deep below you, thousands of miles down, molten iron is churning, swirling, flowing in patterns that generate and sustain the field. All of this is happening simultaneously, a planetary-scale system operating continuously, day and night, year after year, millennium after millennium. You're not separate from this system. You're part of it. Your existence depends on it. And in understanding it, you've become conscious of your place within it. That's a profound shift in perspective. Most animals live their entire lives without ever contemplating the forces that sustain them. They simply exist, responding to immediate stimuli, surviving day to day. But you can do more. You can think about the invisible, understand the complex, appreciate the improbable. You can recognize that you're a temporary pattern of matter and energy, sustained by processes that were ancient before you were born and will continue long after you die. And there's peace in that recognition, because it means you don't have to carry the weight of the universe on your shoulders. The magnetic field doesn't need your help to keep working. The sun doesn't need your permission to keep shining. The laws of physics don't require your belief to remain true. The universe operates according to its own logic, indifferent to human concerns, and you're simply here for the ride. You can let go of the need to control everything, the anxiety about what might happen, the fear of the unknown. Because in the end, you're held by forces far greater than yourself, protected by an invisible shield you didn't create and can't destroy. That's the gift of understanding the magnetic field. It's not just scientific knowledge, though it's that too. It's also a form of reassurance. You're not alone. You're not unprotected. You're wrapped in a magnetic embrace that's been here for billions of years and will be here for billions more. And while your individual life is brief, flicker in cosmic time, you're part of something vast and enduring. The atoms in your body are ancient, recycled from stars that died long ago. And when you die, those atoms will be recycled again, incorporated into new structures, new patterns, new forms of existence. You're a temporary arrangement of stardust, animated by consciousness for a brief moment, then released back into the cycle. The magnetic field is part of that cycle. It's generated by the motion of matter, iron flowing in Earth's core. And that iron came from the same stellar explosions that created the iron in your blood. You and the magnetic field are made of the same stuff, connected by a chain of events that stretches back to the formation of the solar system and beyond, to the deaths of earlier generations of stars, to the birth of the first stars after the Big Bang, to the Big Bang itself. Everything is connected. Everything is one. The appearance of separation, of individual objects existing independently, is an illusion. At the deepest level, it's all one continuous process, matter and energy flowing through space and time according to natural laws. And somehow, in the midst of all this cosmic activity, consciousness emerged. Matter became aware of itself. The universe developed the capacity to observe and understand its own workings. You are that capacity, at least for a brief time. You're a way for the cosmos to know itself, to experience itself, to appreciate its own beauty and complexity. And in learning about the magnetic field, you're fulfilling that role. You're the universe understanding one of its own fundamental features, a protective mechanism generated by one planet among trillions, invisible but essential, silent but powerful. So as you finally surrender to sleep, as your conscious mind lets go and drifts into dreams, let your last waking thought be one of gratitude. Not gratitude to anyone or anything in particular, because the magnetic field doesn't require thanks and wouldn't know what to do with them, but gratitude in the general sense, an appreciation for the improbable circumstances that led to your existence. You're here because countless things went right. The solar system formed with the right mix of elements. Earth coalesced at the right distance from the sun. The planet was large enough to sustain a geodynamo, but not so large that gravity crushed everything. The magnetic field emerged and persisted. The atmosphere formed and was preserved. Life appeared and evolved. Consciousness developed. And through billions of years of cosmic history, a chain of events unfolded that culminated in you, lying here listening to these words, contemplating the invisible force that makes it all possible. Tomorrow, when you wake, the magnetic field will still be there. It will be there the day after tomorrow, and the day after that, for every day of your life. It will be there for your children's lives, and their children's lives, and on into the future. It's the most reliable, most faithful companion you've ever had, even though you've never noticed it, never acknowledged it, never given it a second thought. But now you know, now you understand. And that understanding, that knowledge, is yours to keep, yours to share, yours to carry forward into whatever future awaits. The invisible guardian stands watch, the shield holds, and you, small and temporary as you are safe within it, protected by forces you'll never see, sustained by processes you'll never directly experience, connected to a universe that's vast and ancient and beautiful beyond measure. Sleep now. Let the weight of consciousness lift. Let your thoughts dissolve into dreams. The magnetic field will still be here when you wake. The sun will still shine. The earth will still turn. And you will still be here, alive, breathing, existing within the invisible embrace of the shield that has protected life on this planet for longer than life has existed. The journey is complete. The story is told. And the only question that remains is this. Now that you know about Earth's invisible shield, now that you understand the magnetic field and its role in making life possible, how will that knowledge change the way you see the world, the way you live your life, the way you appreciate each moment you're given? Perhaps you'll look up at the stars with new eyes, knowing that between you and the void stands an invisible barrier, ancient and steadfast. Perhaps you'll feel a deeper connection to the planet, understanding that you're not just living on Earth, but within it, protected by its core, sheltered by its magnetosphere, part of a system that's been operating for billions of years. Or perhaps you'll simply rest easier, knowing that even in a vast and indifferent universe, there are forces working in your favor, invisible guardians that ask nothing and give everything. Sleep well, dream softly, and remember always that you are protected by the invisible, sustained by the unseen, and connected to something far greater than yourself. The magnetic field wraps around you like a blanket, Earth's gift to all who live upon its surface, a silent promise that has never been broken and never will be, for as long as the core still flows and the planet still turns. Good night.